What I'm going to do is I'm going to finish first the tutorial for chapter 4 before I continue the lecture. So today lecture I replace with our tutorial, and then our tutorial on Wednesday. Then I will do lecture of chapter 5. Okay, so today, as you know, in week 8, the lecture hours, sebelum ni in week 1 to week 7, our lecture hours is 3 hours. If you realize, 3 hours lecture, 2 hours tutorial. So starting from week 8, all the lecture time is back to the normal 2 hours. So today class is on schedule pun kalau kamu check ada timetable baru. Please check your timetable if you're not too sure. Memang minggu 7 ke 14 timetable untuk courses with lecture. If before this you have 3 hours lecture, now it's already down to only 2 hours. So our Monday class barat yang sepatutnya 4:30 to 7:30 is now only from 4:30 to 6:30. Okay, so make sure you check for other courses as well. Lecture dia dah tak ada 3 jam, dia dah kurang kepada 2 jam. So tutorial is still the same, 2 hours. Just that lecture now is 2 hours instead of 3 hours. So our class pun hari ni akan habis by 6:30 lah. Okay, I will not go further also lah. Alright, so we will continue with tutorial chapter 4. So sorry, I just uploaded the question this morning. Saya pun lupa to upload the question earlier on, but it's fine. As you know, for my tutorial, I will guide you solely how to do it. Most importantly is for you to really understand the steps, particularly chapter 4, because chapter 4, if you realize, we derive a lot of equation. So equation tu pun dah banyak, and then now sekarang kita nak faham macam mana kita nak apply, how we going to apply to solve the questions using the equation that is provided to us. So as I told you, you don't need to memorize any of the equation. You're not expected as well. It's too many equations. Tetapi the challenge is how are you going to know which equation to be used to solve what kind of question. Okay, so just a feedback for test 1. Actually, most of you done, I would say all of you actually done better than what I expected. So some of you can score even up to, I think, 48 out of 50. So that's almost perfect marks already, which is quite surprisingly. Normally test 1 for the previous semester, students don't normally do that well. So not only one, we have a few that just score very high marks. The rest are okay. Most of you pass. None get 0. I think only a few, none. All of you get above 5 out of 50 marks. So that's actually a very good improvement for test 1. Not improvement, I would say that's a very good achievement in test 1. So you should actually aim, you can and should actually aim for really good grades in reaction lah. You do well in test 1, test 2 and final exam should not be a problem. Okay, mini project, I check some of the mini project got some problems. I think the most problem is I think some groups do not understand the guideline. Actually the guideline I already stated. Okay, memang betul. For example, you are producing the chemical, for example producing methanol ke, acetic acid ke, very rarely it happen in one chemical reaction. Usually you have several chemical reaction. Okay. However, in the guideline I did mention you just choose that one reaction that produce your final chemical. So contohnya mungkin to produce methanol, first maybe your raw material has to produce an intermediate. Intermediate tu baru boleh produce methanol. Contohnya dalam kes ni kamu ada 2 tindak balas lah. Raw material to intermediate to methanol, for example. In your case, when you design the reactor, you just base on the last, on the reaction yang produce methanol itu ataupun tindak balas yang menghasilkan the chemical that you are assigned to. So katakanlah memang tindak balas kamu tu untuk menghasilkan methanol tu started from the intermediate. You assume dalam reaktor kamu tu memang hanya satu tindak balas daripada intermediate untuk produce your final product. You do not need to consider the many reactions. But kalau kamu nak consider the many reaction, it will be very complicated for your reactor design. Okay, so for stage 1 tak apa. As I told you, stage 1 kamu dah siap. You do not need to resubmit. Just that I have to clarify this for your stage 2. Sebab stage 2, your calculation must be based on one reaction sahaja. So make sure if your stage 1, you have listed out the many reaction, just choose that one reaction to produce the final chemical that is tasked to you. Second, I realize a few groups I do understand the sources are obtained from literature. Memanglah benda tu memang datang pada literature. It's not from yourself. However, as I told you, you cannot just cut and paste berpage daripada literature. Okay, so I catch a few groups where not all, I think maybe 1 or 2 isolated groups and 1, 2 isolated members where you basically cut and paste the entire thing from literature. That one cannot. Okay, that one really cannot. So stage 1, I bagi chance lagi. Okay, I will just deduct certain marks for those who plagiarize or basically copy and paste the entire literature tu, I deduct marks. But in stage 2, please do not repeat this. In stage 2, if this is repeated, for that person, your report I will just give 0 straight away. So again, I repeat, stage 1 saya tak bagi 0, I just deduct certain marks. Okay, because I will turn it in all the reports. Okay, so stage 1, I still bagi chance lagi. Even if you cut and paste the entire page, I still deduct certain marks only. But stage 2, this cannot be tolerated anymore. So at least I'm being fair. I give you chance, I remind you. So stage 2, if you cut and paste the entire thing from literature ke, or you cut and paste the entire calculation from someone else, okay, do remember memang turn 18 boleh tangkap semua ni. Okay, so if this is happen again in stage 2, I will give you 0 straight away for the student lah, for part dia lah. Means not, the entire group will not be punished, only for that particular student which plagiarize or cut and paste from other resources. Okay, so I hope this is a reminder. Make sure you don't repeat this in report in stage 2 of mini project, because later on you will continue with FYP. For those process, you will do design project 1 with me. So this cannot be tolerated in other courses as you go further, especially FYP dengan design project. That's why I still give you chance, but please do not do this again, cut and paste. Certain part, kalau certain student dia akan copy here and there, saya faham. Sikit-sikit tu saya boleh terima lagi. Tapi if it's entirely like 5 pages, all 5 pages is cut and paste from one task, from one source, I think it's not fair. Why I punish is because I think it's not fair for your friends who really work hard, who really do the, they read, they interpret, they write it back. I think it's not fair for those friends who work hard. So it's not fair for those who work 5 hours to get the same mark for those who just cut and paste and work 30 minutes. I think that's not a fair comparison. So that's why I deduct the marks in stage 1, but I will give you completely 0 in stage 2 if this is repeated. Alright, okay. So done on the mini project, done on the test. Now I will go also for the test. I detected very minimal, maybe 1 or 2 students who copy each other in test 1. So again, nasib baik yang dia copy tu set yang berlainan. I do a lot of set. Basically, I have 10 set. So I can detect easily when you use number from other set. Okay, so I detected a few students who do this. Test 1, saya bagi chance lagi. Okay, I just deduct mark ataupun basically you dah copy the wrong answer, wrong number, memang dah kosong lah markah for that part. I still give you chance. I did not punish the entire test. But basically, you have already committed plagiarism for the test. So test 1, saya tutup mata lagi. I just punish for that section. I did not give you marks. Okay, memang dah betul salah pula sebab you memang dah ambil nombor lain. Test 2, no more. Test 2, if you plagiarize even 1 part, I will give you 0 for the entire test. Okay, so again, for test 2, if you copy from your friends, I will give your entire test as 0 already. Okay, so again, I dah bagi chance, I give you chance. I remind you, I memang dah catch. Not many, I think 1 or 2 students. Please don't do again in test 2. If test 2, if I catch people copying, regardless the source or the one yang meniru, dua-dua pun dapat kosong. Okay, so it's not fair. Kalau orang tu yang ditiru, dia pun dapat kosong, but I will give you both 0 if I caught any copying in test 2. Right? Okay, so done on the test, done on the reminder, done on the postmortem, on the test and mini project. I will go to your tutorial chapter 4. Okay, so tutorial chapter 4 ni, it's a bit hard because if you remember the question is a bit hard. So I will go slowly. I will explain the steps as we go about the question. Okay, if you want to see the questions, I've already uploaded on the VLE. I already uploaded on the Teams as well. Under the files, we check questions for chapter 4. Right, okay, so go to the question. The first question, the liquid phase reaction below obeys the elementary rate law and is carried out isothermally at 350 Kelvin in a flow system. Okay, so maybe lepas seminggu tu, maybe you forget a little bit. So I will go very slow. Kamu kena faham balik step by step untuk solve question chapter 4. So first of all, dia kata liquid phase reaction. So from now on, by now you already realize the significance of the phase in the reaction when you're solving question. Especially if the phase is important when you're talking about flow reactors, means CSTR, PFR. So bila kamu nak solve question, ada CSTR, PFR, you must really check, is it liquid phase or gas phase reaction? Okay, so dalam case ni dia adalah liquid phase. 1. Second, it says obeys elementary rate law. So by now, you already know, right? In chapter 3 test pun dah keluarkan soalan kalau rate law, elementary, non-elementary rate law. So dia dah kata elementary rate law. By now, you already can write the rate law. Meaning, kalau dia obeys elementary rate law, the reaction orders of the reactant is equal or similar to the stoichiometric coefficient. Kejap saya besarkan. The reaction order of each reactant is equal to the stoichiometric coefficient. So in this example, the reaction is 1A reacting with 1B. We have 2 reactants. So by right, rate law dia will become minus RA. Rate law terus-teruslah, minus RA equals to K. Okay, K tu kita tak tahu lagi suhu dia. We can just put it as K pun tak apa. Then CA power of 1, CB power of 1. So Y power of 1 for A because first order with respect to A. Y first order because stoichiometric coefficient for A is 1. Then CB power of 1 because it's first order with respect to B as well. And Y first order because its stoichiometric coefficient is number 1 in front of B. Okay, so you get the rate law minus RA equals to K, CA, CB. So you know the power of 1, if you don't write also is fine because katakan 5 power of 1 is still 5, 4 power of 1 is still 4. So tak tulis kuasa 1 tu is fine, is understandable, bermaksud dia adalah kuasa 1. Alright, then carry out isothermally. So by now, chapter 4, we still talking about isothermal, means there are no changes of temperature during the reaction. Meaning suhu yang masuk, suhu bahan yang masuk akan sama dengan suhu of your product after the reaction takes place. Okay, so it's carried out at 350 Kelvin. Okay, so suhu tindak balas adalah 350 Kelvin. Okay. When you know already the temperature of the reaction, by right kamu dah terus tahu, means dalam rate law, the value of K mesti pada 350. So kamu ingat, nak design reactor, kita kan ada rate law, minus RA tu. So minus RA tu ada K. K tu, you know, as I taught you, is sensitive to temperature. Dia berubah mengikut suhu. So dia mesti pada, the K must be at our reaction temperature. So if now our reaction at 350 Kelvin, our K must be at 350. So to ensure you don't have this confusion, it's highly recommended untuk tulis macam ni lah, K subscript 350, so that it tells you that bila kita nak buat calculation later, the value of K must be at 350. Any other value or any value of K at any other temperature, it cannot be used to calculate the rate law. Okay, done. Right, so next dia kata, the initial concentration of A and B are 0.05 molar. Okay, so they tahu, now you know initially you got A and B. So they give us the concentration, the initial concentration. So you know initially, initial concentration of my A is 0.05. So Ca naught 0.05. Okay, equals to, since initial concentration of B is also 0.05. So Cb naught also equals to 0.05. So from the test, I can see that all of you are very good. At least kalaupun mungkin tak dapat jawab the question, but you're able to actually extract the information and write down in symbol. So okay, I see like all of you, 30 of you actually have done this very well, means tak ada masalah, kamu faham soalan, kamu dah faham maklumat. Okay, so that's also a very good improvement. So you can write down C naught equals to CB naught equals to 0.05. So that's the information you derive from the first sentence. Then dia kata at 100 liter per minute. Okay, so this one pun, I think dalam test one pun, most of you are able to do. So dah faham kalau liter per minute tu dimension dia volume per time. So volume per time istilah volumetric flow rate. Okay, so kamu tahu dah volumetric flow rate. So since dia kata initial, so you know this is initial volumetric flow rate. So we use epsilon naught. So epsilon naught is 100 liter per minute. Okay, so epsilon naught is the initial volumetric flow rate. Okay, done. So dia kata lagi, it is determined the reaction rate constant is 0.7 liter per mole minute at 300 Kelvin. Okay, so they do give us the K. However, the K yang 0.7 is at 300 Kelvin. Okay, although dia beri kita nilai K, tetapi K ini pada 300 Kelvin. Okay, so if you forget, kalau kamu ingat, the reaction is at 350 Kelvin. So although you have the K, but the K given to us is not at the reaction temperature. Okay, so this is something that you have to be, how to say, you have to catch up lah. Kamu kena betul tahu, okay, suhu tidak balas saya 350. Walaupun saya ada nilai K, but the nilai K, the value of K is not at my reaction temperature. Okay, next. And they give us activation energy. Okay, so activation energy is EA lah. So EA 5 kilocalorie per mole. So from test 1, I can see I will do a little bit of postmortem as I go on so that you know kat mana kamu berada kat sekarang. Okay, what do you do? What do you do right? What do you do wrongly? Okay, so even from test 1, I see that students are able to understand activation energy tu apa, nilai K tu apa. So not bad. So this is also a good progress. You understand the concept of Arrhenius. So kalau kamu perasan nanti as you go on chapter 4, chapter 5, chapter 6, basically dia hampir benda yang sama sebenarnya. Dia bukan repeating. It's stages by stages. So benda yang kamu pakai chapter 2 akan digunakan in chapter 3. Now it's going to use in chapter 4 as well. So it's a progressive understanding. Right. So done. That is all information given to us. So by right, until by now, you should be able to do this. Okay, maknanya the first 2 line of information tu kamu dah boleh synthesize, kamu dah boleh extract daripada soalan information dalam bentuk simbol. So you know what you are given and what is not yet known to solve in the question. Okay, so let us go to the question. Question A says, a 500 liter continuous stir tank reactor, CSTR, and an 800 liter plug flow reactor, PFR, so are available for the reaction. So imagine in your plant, okay, you have 2 reactors, which is a CSTR of a 500 liter and an 800 liter of a PFR. Okay, so you have 2 separate reactors. So they ask you which reactor is recommended for the reaction. So dia tanya kamu, reaktor mana yang kita nak guna untuk tindak balas ini? So they give you the information, they give you the volume of the reactor, then the question is very simple. Reactor mana yang kita nak guna? Okay, so how do we do this? So you know, in engineering, in science, our decision is always based on something quantitative ataupun our decision must be based on a number. Okay, so apa tu number dia? Macam mana kita nak tahu nombor apa yang kita nak gunakan untuk compare? Okay, so you do understand that when we talk about reaction, the most important thing is always we talk about conversion. Sebab preferably, ideally, we would like to have as high conversion as possible. Sebab conversion tu kan merujuk kepada reactant A. The higher conversion, meaning the more A is converted. The more A is converted, of course you get more product. Okay, so by right, how we want to compare which reactor is better is actually by comparing the conversion, meaning we have to know the conversion in the 500 liter CSTR and we compare to the conversion in an 800 liter PFR. So by right, which reactor that give us the higher conversion shall be the selected reactor ataupun the reactor that we recommend. Okay, so how do we do this? How do we determine the conversion? Okay, so Kamu tahu, kita dah belajar chapter 4 kan? Chapter 4, we have learned equation that relates the volume to conversion. Tetapi equation yang mana nak digunakan? Alright, so I will first teach you the equation first. Okay, so of course you don't need to actually memorize. Okay, tapi yang penting kena tahulah kan mana equation yang nak digunakan. Okay, now we talk about first. Kamu tahu this is flow reactor. So bila sampai flow reactor, maksudnya PFR, CSTR, equation dia dah berubah depending on liquid phase or gas phase. Okay, so di pertama kena tengok the reactor type. Second, of course you kena tengok whether it's a liquid or gas phase. Third, kamu kena tengok rate law. So dalam kes ni, dia kena cari equation that fulfills 3 requirement. Okay, so first, reactor dia. Okay, let us first start with CSTR lah. We talk about CSTR first. So, when you check the note, kamu kena tengok dulu. Of course, kamu tengok dulu lah notes untuk cari equation CSTR. Okay, first. Second, kena tengok liquid phase ke gas phase. So dalam notes equation tu I have already explained to you perbezaan equation bila liquid atau gas. So you look CSTR, liquid as given in this example. And third one, tengok rate law. So equation yang kamu pilih tu mesti memenuhi these 3. CSTR, liquid phase dengan rate law dia mesti KCA-CB. Kamu tak boleh tengok rate law KCA. Kamu tak boleh tengok rate law KCA square. Itu adalah bukan rate law yang betul. Kamu kena tengok untuk rate law KCA-CB. Okay, alright. So, if you check the equation correctly, by right, you will see there's only one equation yang matching kepada these 3 requirement, which is given as volume CSTR equals to FA0 X in bracket over K CA0 1 minus X CA0 in bracket 1 minus X. Sorry, this is derivation. I terus pergi to the last one. By right, this is the last equation. My steps ni tunjuk macam mana kita nak derive. Okay, but you're not expected to derive. You don't need to show the derivation. Yang penting is the final equation. Okay, so by right, if you look at this correctly, yang final equation that fulfill these 3 requirement is only one equation, which is given as epsilon naught X CSTR conversion over K. I write 350 terus suhu tindak balas 350 CA0 in bracket 1 minus X CSTR tutup bracket power of 2. Okay, if you remember, I teach you design equation ni ada few version. Kenapa? Sebab certain version if you know FA0 and CA0. Another version if you know epsilon naught. These 2 version is to find volume, and you have one more version to find the space time. Okay, so biasanya equation ni akan ada 3 version bergantung kepada apa yang kita nak cari. Okay, ataupun apa yang kita ada, maklumat apa yang kita ada. Okay, in this case, I use the second version of the equation because we are given epsilon naught in the question. Sebabkan soalan kita given the initial volumetric flow rate epsilon naught, so I use the version yang ada epsilon naught. Okay, so later or now, if you have the notes with you, kamu tengok CSTR liquid rate law minus RAK CACB. Basically, this is the equation that you will find and you will use to solve the problem. Okay, so now kamu dah tahu equation yang nak digunakan. So next part is kamu kena gantilah dalam information dia, sebab in this question, they give us the volume. They want us to find conversion. Kan kita nak compare conversion. So maksudnya dalam equation ni, the rest of the unknowns you have to solve except for X. Sebab X tu yang kita nak cari. So maksudnya, you need to know the volume. You need to know epsilon naught, you need to know K, you need to know CA naught, and you are left with the X only. Barulah kita boleh solve untuk tahu how much is the conversion in the CSTR. Okay, so Let us do one by one. Okay, so first, volume of CSTR. In this question, did I mention the volume of CSTR is 500 liter. So left hand side, I already know the value is 500 liter. So right hand side pula. So right hand side, first of all, epsilon naught, the volumetric flow rate, the initial volumetric flow rate, which we already know as 100 liter per minute from the question. Okay. So X, we leave it as it is sebab kita nak cari X. At the bottom is now K at 350. So kamu kena ingat. Satu you, K mesti pada reaction temperature. However, the K given to us, 0.7 is at 300 Kelvin. 300 Kelvin, right? Sorry. 300 Kelvin. Okay, so meaning you have to first find the K at 350. Okay, so this is not new to you. You already know if I know K1 at T1, meaning K 0.7 at 300 Celsius, 300 Kelvin, I can know the K at 350 Kelvin. So tahu K1, T1, kamu boleh cari K2 at T2. So K1 0.7, T1 300 Kelvin, T2 350 Kelvin, bolehlah kita cari K2. So the equation, Arrhenius equation is given, Arrhenius kan ada dua version kan, kita guna version yang kedua, which tell us K2, K at 350 equals to K1, K at 300, exponential EA per R in bracket 1 per T1 minus 1 per T2. So in the test 1, there are actually question number 2 yang menggunakan equation ni, and there are few students who dia dah tertukar. So dalam bracket ni kamu kena ingat dia adalah 1 per T1 minus 1 per T2. So a few student dia terbalik, dijadikan 1 per T2 tolak 1 per T1. So tak dapat jawapan lah. Okay, so make sure you check. Dia mesti 1 per T1 minus 1 per T2. So how to know to check sama ada kamu buat betul ke tak? Kalau kamu terswap, definitely your value of your K will be negative, or kamu tak boleh exponent ke sebab nanti exponent kamu akan jadi exponent yang negatif. So by right, dia takkan dapat yang betul lah, jawapan yang betul lah. So make sure you do it correctly. Dia mesti dalam bracket 1 per T1 minus 1 per T2. So clearly mark T1 tu apa, K1 tu apa, T2 tu apa, K2 tu yang kamu nak cari. So jangan tersilap lah. Alright, so if you calculated correctly, EA is already given. Activation energy dah diberi sebagai 5 kilocalorie per mole. So by right, you know right, because our gas constant, we use 1.987 calorie per mole Kelvin. So your calorie from kilocalorie, you have to change to calorie lah. So how to change? Just multiply with 1000. Okay, you already get from kilocalorie to calorie. Okay, right. So if you do this calculation correctly, you will get the K at 350 as 2.32. Okay, so again, for you to check, katakan kamu tak sure pengiraan kamu betul ke tak, as I taught you, K increases with temperature. So maksudnya K pada 350 must be bigger than K at 300. So you can see at 300, K is 0.7. At 350, the calculated K is 2.32. So somewhat logic sebab K tu nampak naik dengan suhu. So although we cannot conclusively cakap jawapan tu betul, but logically the answer makes sense. So most likely jawapan tu adalah betul lah, right? Okay, so when you calculated this, alright, so you can replace the K at 350 as 2.32. Okay, CA0 dah diberi sebagai 0.05. So you can just replace 0.05. And then in bracket, the 1 minus X CSTR tu masih ada sebab X CSTR tu kita nak cari. Okay, so now you can see from the equation, very simple. Mathematics, kamu tahu satu equation kalau kita nak solve mesti ada satu sahaja unknown. So dalam soalan ni kamu nampak satu unknown je, X CSTR. Walaupun dia muncul di atas dan di bawah dalam equation, but it's still one type of unknown. Okay, dia boleh muncul di mana-mana dalam equation, tetapi dia hanya satu jenis sahaja unknown. So in this case, although the X CSTR is ada ke atas, ada di bawah, tetapi dia ada pada jenis yang sama, you can actually solve this equation. So make sure later when you have time, please try to solve this by yourself sebab dalam equation ni ada quadratic. Okay, I would like you to practice juga how to solve quadratic equation. Okay, so when you solve this, okay, you will get actually two value of x, quadratic kan. So when you have this quadratic equation, when you solve, later kamu akan dapat dua nilai x. Okay, salah satu daripada nilai x tu is more than 1 and another x will be less than 1. Okay, so of course, you know, ideally, theoretically, conversion cannot be more than 100% ataupun 1. So of course X yang lebih daripada 1 tu dah takkan dapat diterima sebagai jawapan. So by this qualification, the X less than 1 will be your final answer. Okay, so again I repeat, when you solve this will be a quadratic equation. So you know dalam maths, kalau quadratic mesti ada dua nilai X kan. So when you calculate, okay, either using calculator or manually, you will get 1X more than 1, 1X less than 1. Okay, so by theoretically disqualifying the X yang lebih daripada 1 sebab conversion tak mungkin more than 100%. So of course you will choose the 1 less than 1 which is 0.29. Therefore the conversion for your CSTR is 0.29. Maksudnya in your 500 liter of your CSTR, the highest conversion possible hanyalah 0.29. Okay, so we finish for the CSTR. So again, okay, mungkin saya faham kamu baru semester break and saya tahu chapter 4 tu banyak sangat equation. Okay, tapi yang penting S1U, yang penting kamu kena tahu nak pilih equation yang betul. Macam mana nak tahu tu? S1U tengok soalan, check 3 benda ni. Satu, jenis reaktor, dia mesti CSTR. Benda yang kedua, check dia mesti liquid phase. Kalau gas phase, equation dah berlainan. Ketiga, check the rate law. Rate law dalam soalan ni minus RA sama dengan KCACB. So, kamu cari equation yang fulfill these three, betul lah equation tu. Tetapi kalau equation kamu pilih itu tak memenuhi salah satu pun, your equation will be wrong. Okay, so yang penting dalam to solve this is actually really knowing the right equation based on the criteria that I've already told you. Okay, so next we go to PFR. So sekarang kita pun nak comparison kalau we use a 800 liter PFR. So sama konsep. Okay, of course lah equation tadi kita tak boleh gunakan. Kenapa? Sebab walaupun dua syarat tadi masih sama, liquid phase is still the same. Liquid phase masih sama, rate law masih sama kan? Dua tu syarat masih sama. Tetapi equation dah berubah. Kenapa? Sebab jenis reactor is now PFR. So kamu nampak kan, walaupun kita ada 3 kriteria, 2 masih sama, 1 dah berubah, equation dah berubah. So kamu kena check pula sekarang, PFR, liquid phase, rate law minus RA, KCACB. So nanti bila kamu nak test, final exam, the challenge is betul-betul tengok equation mana yang untuk digunakan. Okay, if you check it correctly, by right the equation will be this one. Okay, equal volume PFR equals to epsilon naught over K 350 Ca naught in bracket X PFR per 1 minus X PFR tutup bracket. So check equation, tengok mana satu. Okay, after this you have time. Sebab kamu ingatkan chapter 4 ada 30-40 equation. So betul-betul kena tengok equation mana yang fulfill these 3 requirement. It's only one equation. Tetapi lepas tu kamu tengok kan, dia ada version yang berlainan. So S1U version tu berlainan sebab dia bergantung kepada information. So version 1 and 2 untuk cari volume. Just that version 1 tu kalau kamu ada FA naught, version 2 tu kalau kamu ada epsilon naught. And version ketiga tu untuk cari space time. So untuk soalan ni, dia beri kita epsilon naught. That's why I use the second version yang ada epsilon naught. Okay, so version 1, version 2 ni bergantung kepada maklumat yang diberi. Adakah they give you FA naught or they give you epsilon naught. Okay, now that you have the equation, So the same concept, we replace with a numbers sebab again kita nak cari conversion. The rest tu mestilah diganti dengan nilai. Okay, so on the left hand side, volume of PFR 800 liter given in the question. Okay, right hand side. Alright, first of all, atas dia ada epsilon naught. So epsilon naught is 100 liter per minute. Okay, so 100 liter per minute is your initial volumetric flow rate. Alright, so bottom. K at 350. K dia. K dia. Okay, the K at 350. Hold on, let me. Okay, so it's K at 350. Okay, if you don't change your temperature, of course your K is still the same. Okay, so kamu kena faham. Walaupun kita berubah reactor, asalkan kamu tak ubah suhu tindak balas, the K is still the same. So kamu kena faham konsep apa yang berubah dengan reaktor, apa yang masih sama. So nilai K ni hanya bergantung kepada suhu tindak balas. Okay, dia tak dipengaruhi oleh jenis reaktor yang berlainan. So nilai K masih sama, you will use 2.32. Okay, next is your Ca0. So Ca0 masih sama, the initial concentration is still the same. Alright, so kita ganti masa yang sama. So in the bracket is still now left with the X PFR, the one that we want to find. So the X is remain, the rest you replace with numbers. And when you calculate, okay, yang ni quite straightforward, tak ada quadratic. Okay, so kamu boleh solve ni lebih straightforward lah. CSTR tu a little bit complex. So make sure memang soalan cikgu tempat ni akan student will take a lot of time sebab ada quadratic lah, ada pindah here, pindah there lah, a bit complex. However, if you do it correctly, you will get the conversion of the PFR as 0.48. Yang ni tak ada quadratic. Satu saja X yang kamu akan dapat, which is 0.48. Okay, now that you obtain the conversion from the CSTR, the conversion of the PFR, you don't forget you need to answer the question. The question katanya which reactor to recommend. So kalau kamu perasan dalam soalan, dia tak suruh pun kamu cari conversion. Tetapi in order untuk menjawab soalan dia tu, kamu kena intrinsically ataupun secara tidak langsung kamu kena tahu untuk menjawab soalan tu saya kena cari conversion, saya kena kira conversion, baru saya boleh jawab soalan tu. Okay, so by comparing the conversion, okay, we recommend the use of a plug flow reactor as its conversion is higher than CSDR. So jangan lupa kalau soalan tu suruh jawab, you must answer by comparing the conversion. PFR is the recommended reactor due to its higher conversion. So kamu jangan ingat, kamu jangan lupa. Kamu kena jawab soalan tu. So kamu dah kira, betul kamu recommend. Okay, kenapa kita recommend PFR? Sebab bila kita kira conversion PFR is higher than conversion CSTR. So that's for question 4. Sorry, let me make it bigger. So this is the question for part A. So you can see it's quite long kan cara pengiraan dia sebenarnya macam saya, sebab saya tunjukkan sekali cara nak derive equation. Okay, tapi untuk kamu untuk jawab test, untuk jawab exam, kamu tak payah pun derive equation dia. Yang penting kamu terus tahu nak guna final equation and replace the correct numbers to solve the problem. Okay, so I will give you about 1 minute as usual lah. Setiap soalan I will give about 1-2 minutes. If you have time, katakan kamu nak refer kepada soalan ataupun notes, I give you 1-2 minutes. I will come back after 2 minutes and we will continue to the next part of the question. Right. Right, so we will go to the next question. Alright, so we are done question A. Memang if you realize question chapter B, chapter 4 ni the question is very long, the solution also is quite long, right? So to question B, right, to increase the conversion from the first continuous third tank reactor in part A above, the technologists decided to add another equal volume continuous third tank reactor to the first continuous third tank reactor in the series. Therefore, determine the overall conversion from the second continuous third tank reactor. Okay, so hold on. So kalau tengok soalan tu penting kan? So apa sebenarnya soalan tu nak? So soalan tu kata, part A tadi kita dah guna CSTR. Okay, you realize from part A, the conversion is only 0.29, 29%. So you know, right, 29% is quite low. So what they do is, they connect another CSTR to the first CSTR in part A. And then the second CSTR pun sama equal volume. So means 500 liter CSTR connected to the second 500 liter CSTR with the hope we can increase the conversion from 0.29. Okay, so ditanya, what will be the overall conversion from the second CSTR? Okay, so part ni kamu dah kena be very careful sebab sekarang soalan kata saya ada 500 liter CSTR yang I calculated in part A, I only get 29% conversion. So I connect to the second CSTR, so means my second volume CSTR, VCSTR2 tu masih 500 liter and I want to know the conversion kat second reactor. So of course dia akan naik lah kan daripada 0.29 to what value? From X1 to X2, dia nak kita cari berapa X2 itu. So X1 kita dah tahu 0.29, kita nak cari X2 tu berapa. Okay, so if you realize, soalan ni, I do not touch reactor in series kat chapter 4. Tetapi I do touch reactor in series in chapter 2. Okay, so sekarang kamu kena have to understand how do we relate apa yang kamu belajar di chapter 2 dengan apa kamu belajar di chapter 4. Okay, so dalam chapter 2, beza dia adalah, okay, kamu dah pernah belajar we connect reactor in series. So kita pun dah belajar kan macam nak cari volume pada kita ada reaktor pertama dan kita nak cari volume pada reaktor kedua. Okay, let's say kamu confused. Macam mana kita nak relate chapter 2 dengan chapter 4? Sebab dalam chapter 4 memang saya tak touch langsung pasal reaktor berseries. Okay, so how do we correlate chapter 2 and chapter 4? Right, in chapter 2, you have learned, okay? Kalau kita nak cari volume for second CSTR, kamu kena faham, saya kena ajar ni by detail sebab memang equation, final equation untuk soalan ni tak ada dalam notes. So, kamu kena faham macam mana kita correlate chapter 2, chapter 4 untuk kita dapatkan final equation ini. Okay, dalam chapter 2, you have learned nak cari volume second CSTR, dia lah sama dengan FA0 in bracket X2 minus X1 tutup bracket per minus RA2. Okay, yang ni pun kalau kamu perasan dalam test 1 ada soalan yang I did ask you question for reactor in series and some of you saya rasa tak check equation betul-betul. Okay, memang betul. Kalau reaktor pertama memang formula dia VCSTR1 FA0 X1 per minus RA1 if it's the first reactor. However, when it's a second reactor, formula dia jadi volume CSTR2 equals to FA0 in bracket X2 minus X1. Some of you, quite a number of you, saya rasa terlupa, kamu letak terus FA0 X2. Salah dia bukan FA0 X2, dia lah FA0 in bracket X2 minus X1. Okay, so don't forget. Part ni, I think a few of you, quite significant numbers do this mistake. Equation tu dia tersalah tengok ataupun dia mungkin dia terus assume kalau reaktor pertama FA0 X1, reaktor kedua FA0 X2. No, reaktor kedua FA0 in bracket X2 minus X1 per minus RA2. Okay, so dalam chapter 2, kamu belajar yang kita tahu X2, kita tahu X1, kita tahu FA0, kita terus minus RA2 tu kita tengok daripada table kan. Means kalau kamu tahu X2, kamu tengok table atau kamu tengok plot, kamu terus tahu berapa nilai minus RA2. This is what you learn in chapter 2 yang mana you don't need to calculate minus RA2. Okay, sebab dah diberi table, dah diberi plot, Levenspiel plot. However, untuk chapter 4, untuk soalan ni, kalau kamu perasan, they do not give us any table or they do not give us any Levenspiel plot. Meaning, saya takkan tahu berapa nilai minus RA2 itu. Walaupun, and also, saya pun tak tahu X2 kan, saya nak kira X2. So, X2 saya pun tak tahu. And of course, by default, minus RA2 pun saya tak tahu. Because I don't have table, I don't have Levenspiel plot. So, this is where chapter 4 kena masuk balik. Okay, kamu kena faham pula pengetahuan dalam chapter 4. Just now, kita dah derive rate law kan? Kita dah derive dalam part A. Dalam part A, we say the rate law minus RA equals to K, CA, CB. Okay, sebab itu adalah, untuk part A adalah 1 CSTR, 1 PFR, rate law dia minus RA equals to K, CA, CB. Sekarang, we have to derive. Apa pula rate law sekarang kalau dia adalah dalam reaktor yang kedua? So, jadi minus RA2. Minus RA2 adalah rate law dalam reaktor yang kedua. Tadi yang kita derive tu adalah rate law untuk reaktor yang pertama. So, apa beza dia? Okay, so kita kena faham perbezaan dia lah. Okay, so now the rate law become minus RA2. You have to write down. Kenapa kita tulis yang kedua? Sebab sekarang kita nak kira rate law minus RA2 dalam reaktor yang kedua. So, minus RA2 equals to K. Again, regardless reaktor pertama, reaktor kedua, asalkan the temperature tak berubah. If the temperature does not change, the value of K will not change. So, kamu tak payah bimbang reaktor yang berapa banyak reaktor pun, berapa jenis reaktor pun, asalkan suhu tindak balas tak berubah, the value of K is still the same that we calculated previously, which must be the K at 350. Okay, so K masih sama. Okay, what about concentration? Kita kan tadi ada KCACB kan? Okay, CACB tu kamu kena ingat sekarang we are talking about the concentration of A and B in the second reactor. Okay, of course concentration dalam second reactor takkan sama dengan concentration pada reaktor yang pertama sebab as it goes to the second reactor, of course concentration dia dah berkurangan. So we will write it as Ca2CB2 to indicate concentration of A and concentration of B in your second reactor. Dah bukan reaktor pertama, tetapi concentration dalam second reactor. So naturally, concentration dalam second reactor tak sama dengan concentration dalam first reactor sebab kan dia dah consume, di dalam reaktor pertama dia dah consume certain part, certain amount. Dia akan pergi pada reaktor kedua, dia akan consume lagi. So you have to learn how to derive concentration pula. Okay, so part ni yang susah sikit sebab dia macam pemahaman chapter 2, kita gunakan pemahaman chapter 4, kita combine. Okay, sekarang kita kena tahu pula macam nak cari Ca2, Cb2. Apa beza dia? Okay, so Ca2, kalau kamu dah belajar, kita pernah belajar. Kalau kita nak cari Ca, if you want to find Ca, equation dia untuk liquid phase, okay, Ca equals to Ca0 in bracket 1 minus X. Kita dah baca. We have learned already kalau nak cari concentration. Ca equals to Ca0 in bracket 1 minus X. Okay. Hence, kalau saya nak cari Ca2, I want to find the concentration of A in the second reactor. Apa beza dia? So, dia akan menjadi Ca0 masih sama dalam bracket yang berubah. Sebab sekarang dalam bracket ia jadi 1 minus X2. Okay, so kenapa X2? Sebab concentration in the second reactor of A is depending on the conversion in the second reactor. So kalau reaktor pertama, kita tulis Ca sama dengan Ca0 in bracket 1 minus X. Conversion dalam first reactor. So kalau dah ke reaktor yang kedua, so we have to write lah Ca0 in bracket 1 minus X2. Okay, so sama. Untuk Cb pun, we have to write it back. Okay, so kalau kamu forget macam mana kita nak tulis, okay, let me write back equation yang asal. Okay, because I didn't show you this. I will write back the original concentration punya equation. Kalau part ni kalau kamu lupa sikit, chapter 3 kita dah belajar macam nak derive concentration dia. Tapi I will teach you slowly again. Okay, so kalau kamu ingat nak mencari saya kena letak balik. Kalau kamu ingat, kalau kita nak mencari concentration of B as a reactant, dia sama dengan Cb. Saya ajar single dulu. Kalau concentration untuk B as a reactant, Cb sama dengan Ca0 in bracket theta B minus B per A X. Itu adalah kalau dia adalah satu reaktor sahaja. However, now when I'm calculating in the second reactor, apa yang berubah kepada CB? So CB2 now become CA0. CA0 masih sama. So kalau kamu confused, kenapa masih CA0 walaupun reaktor kedua? Sebabkan kami ingat kita kan kira based on conversion. Conversion dia tak reset. Conversion is always based on the original concentration yang kamu mula-mula prepare pada reaktor yang pertama. Yang masuk awal-awal pada reaktor pertama, itu concentration yang kita gunakan untuk kira conversion. So conversion tu based on the very first CA0. That's why CA0 tu yang tak berubah. Okay, so CA0 in bracket theta B minus B per A X2. Okay, so this part yang sekarang kita kena Y now dah jadi X2 sebab kita kira concentration B dalam second reactor of which the conversion in the second reactor is now X2. Kan ingat dalam reaktor pertama 0 to X1, reaktor kedua X1 to X2. Okay, sebab tu sekarang menjadi X2. So kita kira one by one. Okay, part theta B. Okay, so part theta B kalau kamu ingat, okay, dalam soalan dia kata initial concentration of A and B are 0.05 molar. Maksudnya CA0 equals to CB0 equals to 0.05. Hence, your theta B, kalau kamu ingat, theta B akan sama dengan CB0 over CA0. Theta B is initial amount of B over initial amount of A. So, kalau CB0 0.05, CA0 0.05, so theta B mestilah 1. Okay, so that's why your theta B becomes 1. What about B per A? B per A pun akan menjadi 1. B per A itu adalah your ratio of your stoichiometric coefficient. So, ratio of stoichiometric coefficient, B dia 1, A dia pun 1. So, that's why you get B per A to 1. So, CB2 is equal to CA0 in bracket 1 minus X2 because my theta B is 1, my B per A is also 1. Okay, so happen so kamu ingat. So happen dalam kes ni theta B saya 1, B per A saya pun 1. Sebab tu saya dapat CB2 sama dengan CA0 in bracket 1 minus X2. Right, so when you have this already, okay, then what you do next? Okay, so sekarang kalau sebelum ni minus RE2 tu kamu terus check daripada table. Tapi sekarang dah tak boleh kan? So kita kena ganti dengan rate law yang kita dah tahu which is minus RE2 equals to K350 CA2 CB2. Atas masih sama, it doesn't change. It's still FA0 in bracket X2 minus X1 tutup bracket. Okay, so next. So then kita replace CA2 as CA0 1 minus X2 and we replace CB2 as CA0 1 minus X2 again. So happen yang CA2 tu sama dengan CB2. Okay, sebab tu kita tulis dua kali. Kamu tengok kenapa tulis dua kali benda yang sama. So happen dalam kes ni CA2 sama dengan CB2. Right, so the top is still the same. Right, so then next, okay. In this question, kalau kamu perasan dia tak beri kita FA0, dia beri kita V0, epsilon naught. They give us the initial volumetric flow rate. They didn't give us the initial molar flow rate. So what I do is, okay, you know, kalau kita ada satu FA0 di atas, we have one FA0 at the top, we have one CA0 at the bottom, this can be divided. So if FA0 divide by CA0, you get epsilon naught at the top. So now saya dah remove FA0 sebab saya bahagikan satu FA0 di atas dengan satu CA0 di bawah, I will get epsilon naught. So now saya dah ada epsilon naught. In bracket, X2 minus X1 ni masih ada. Okay, at the bottom, kamu jangan lupa the K is there and satu lagi CA0 tu masih ada. Kita hanya berjaya divide satu ataupun kita berjaya cancel satu CA0, satu lagi CA0 masih ada and in bracket now become 1 minus X2 power of 2 sebab 1 minus X come from the CA, another 1 minus X come from the CB. So bila dia is multiplied, it become power of 2. Okay, so now kamu dah, apa yang kamu buat sebenarnya, kamu dah derive equation to find the volume of the second CSTR. Okay, katakanlah kamu confused. Okay, let me compare dengan tadi yang kita gunakan. Tadi yang kita gunakan equation untuk satu single CSTR. Kalau kamu perasan, kamu guna equation ni untuk satu single CSTR. So, apa beza dia yang ini dan yang tadi yang kita derive untuk second CSTR? Basically, kalau kamu tengok apa yang beza dia, di atas kalau single terus epsilon naught X CSTR. Kalau satu, reaktor pertama. When it become ada reaktor yang kedua, dia akan menjadi dalam bracket tu X2 minus X1. X CSTR2 akan minus X CSTR1. So let's say kamu confused. X2 tolak X1 ke X1 tolak X2? Just remember, conversion akan meningkat dengan reactor. The more reactor you go, the higher conversion it will be. So X2 must be bigger than X1. So kalau kamu letak X1 tolak X2, of course volume tu jadi negatif. Kamu tahu reactor tak mungkin volume negatif. So mesti, that's why you know that kamu tulis, you will write in bracket X2 minus X1. Tu benda yang pertama. Perubahan yang kedua, pembawa dia. Tadi pembawa untuk reaktor pertama, when I have one reactor, dia menjadi, yang depan tu masih sama. K C0 tu masih sama. Yang dalam bracket ni, kalau tadi, kalau satu reaktor sahaja is 1 minus X1. Technically 1 minus X1 ataupun 1 minus X. Conversion dalam reaktor pertama. Tetapi bila we talk about second reactor, dia sekarang dah menjadi 1 minus X2. Tu saja beza dia. Equation ni berubah bila we talk about reactor volume for one reactor, or we are talking about reactor volume for the second reactor. Pengatas dia berubah, pembawa dia pun juga dah berubah. So you have to really understand how this happens. Okay, so as I repeat again, equation ni memang tak ada dalam notes sebab tapi kamu dah belajar half of it in chapter 2, half of it in chapter 4. So this question actually combines the knowledge that you have from these two chapter untuk kamu derive equation yang baru. Okay, alright. Now, come back to the main point. Apa yang kita nak sebenarnya? Dia kan nak kita cari X2 sebab dia kata reaktor kedua tu equal volume. Okay, saya tambah satu lagi 500 liter CSTR untuk the second reactor. We want to find out what is the conversion now when we add another second reactor of a 500 liter. So technically on the left hand side, volume second reactor masih 500 liter sebab dia kata dia add another equal volume CSTR. Maksudnya for the second CSTR, the volume is also 500 liter. Alright, so then in the question, okay, dalam equation, volumetric flow rate, initial volumetric flow rate still tak berubah. Again, volumetric flow rate masih sama sebab kamu ingat kan, dia kan continuous. So I will only use one pump to pump the same amount sebab amount yang sama akan masuk pada volume, masuk pada CSTR pertama, and then for the first CSTR, they will flow to the second CSTR. Means antara CSTR pertama dan yang kedua, saya tak kacau flow rate. Dia masih flow rate yang sama. That's why the initial volumetric flow rate is still the same. So in bracket, X2 is what I want to find. So I leave it. X1, kita dah tahu in the first CSTR, the conversion is only 0.29. So saya letak 0.29. Bottom, K, the one that we calculated at 350. Okay, CA0, same CA0, 0.05. And in bracket, 1 minus X2. X2 we want to find. So the X2 we must leave as it is. So again, you realize in this equation, semua dah ada nilai kecuali X2 which we want to find. So you can solve this. Again, this is also quadratic equation. So later I will give you about 2-3 minutes kalau kamu ada calculator. I think if you still do not know how to solve quadratic by calculator, I will highly advise you to start learning macam nak guna scientific calculator to solve quadratic. You may use manual equation yang negative B plus minus punca kuasa B kuasa 2 tolak 4AC over 2A. Itu pun boleh. You can also use that formula. Tapi using calculator is a much faster way if you know how to use calculator to solve quadratic. So please try to do this later. I will give you about 2-3 minutes. To solve this, again, you will have two value of X. Which one will be more than 1, another one will be less than 1. So by default value of X in terms of reaction engineering, kamu kena faham memang value maths tu, memang value tu betul. Tetapi in terms of reaction engineering, in terms of teori yang kita belajar sekarang, conversion tak mungkin lebih daripada 1. So kamu kena faham mathematics, how the mathematics in tandem with chemical engineering. Memang nilai yang lebih daripada 1 tu, matematik kata jawapan tu betul, which is correct. That value more than 1 mathematically is right. However, when you combine with reaction engineering knowledge, kamu tahu kita nak kira yang nilai itu adalah nilai X, conversion. So, conversion tak mungkin lebih daripada 1, not more than 100%. That's why you will disqualify the one more than 1, you will choose the one less than 1. So, the X will be 0.46. So, means from the first reactor, conversion hanya 29%. Dalam second reactor now, the conversion increase substantially to 46%. So let's say you calculate, katakan X2 kamu tu lebih kurang daripada X1. Means X1 0.29, your X2 must be more than 0.29. If you get less, please check back again. It's not possible sebab conversion tak boleh turun, conversion tak boleh reset. Conversion must increase from the very first reactor. Okay. So as I said, I give you about 2 minutes. If you have calculator or if you do it manually, just take a little bit of time, tengok practice, tengok boleh tak kamu solve equation kuadratik ini. Okay, so I will come back in 2 minutes time. Right, okay. So I hope you have time to solve it. Tapi tak apa, if you don't have time pun, nanti later you can try it on your own. So as usual lah, my tutorial question, I have the final answer. So make sure that you really try to do it on your own and tengok faham ke tak faham soalan dia. Right. So to the next question. Right. So soalan satu ni panjang soalan ni panjang soalan. Okay. C. Determine the reaction time when the reaction is conducted in a batch reactor to achieve the conversion of 48%. So sekarang dah berubah pula. Sekarang dia kata batch reactor pula. So kamu kena tengok rate law masih sama, phase masih sama, but the reactor is now changed. Now I'm using batch reactor. And then dia nak kita cari reaction time. Okay, so dia suruh kita cari reaction time dalam batch reactor. So kalau kamu terlupa, when we talk about PFR, CSTR, we talk about sizing. We talk about the volume of the reactor. However, when we talk about batch reactor, we will talk about in terms of reaction time. Kita nak tahu kalau kita guna batch reactor ni, how long we need, okay, for the reaction to be conducted. Right, so sama je konsep. senang saja. Tengok balik notes. Okay, so the same. It's the same thing that you apply later when you go to the workplace, when you join the industry. You have to do calculation. You don't have to memorize the equation, right? Kamu just kena make sure kamu tahu equation yang betul untuk digunakan. So go back to your notes, check. Must fulfill these 3 requirements. First, dia mesti batch. Second requirement, liquid phase. Kalau batch tak payah bimbang sangat. Sebab for batch, liquid or gas is still the same equation. Okay, so kalau PFR, CSCR, kamu kena betul-betul check for the phase. Kalau batch, satu bentuk dah senang lah. Fasa tu, regardless of the phase, the equation is still the same. Third, kena check rate law jugalah. So make sure you check the rate law. Okay, so if you check correctly, all these 3, there's only one equation that will fulfill this requirement. So equation dia given as reaction time equals to 1 per K Ca0 in bracket X per 1 minus X. So only one equation yang akan fulfill ketiga-tiga requirement ini. Okay, so ada equation tak akan dapat fulfill ketiga-tiga requirement ni, only one equation. Okay, so from this equation, kamu solve sajalah, very senang kan? Kita dah check reaction time. So left hand side is what we want to find, reaction time. So right hand side, by right, ketiga-tiga unknown X, K, Ca0, kita kena ganti dengan nilai. Okay, so K masih sama, tak berubah suhu, K is still the same, Ca0 is still the same, initial concentration delivery, X delivery. Dalam soalan ni, our X is 0.48. So don't forget, dalam test pun very isolated cases, tapi ada juga case yang student tersalah, dia tak tukar percentage to fraction. So kamu kena ingat, memang dalam soalan kadang-kadang we report conversion in terms of percentage, okay? But in calculation kamu kena tukar percentage tu dalam bentuk fraction. So kalau 48% dalam bentuk fraction ataupun dalam bentuk perpuluhan lah, biasanya saya cakap dalam bentuk perpuluhan, dia akan menjadi 0.48. So replace your X 0.48. Okay, you replace everything, you should be able to get the reaction time as 7.96 minutes. Okay, so this is not hard. Okay, batch reactor ni tak susah, soalan ni quite straightforward. Just that kamu kena faham lah, kamu kena carilah equation yang betul. Okay, so kalau dapat cari equation yang betul, you can replace it correctly. So the challenge in question number 1, part B tu a little bit challenging sebab part B tu kita dah belajar pasal cycle reactor. Tapi part A challenge dia nak faham apa yang kita kena kira. C is quite straightforward. Tahu batch reactor, tahu equation mana, dah boleh cari reaction time. Okay, so I will straight away go to part D sebab dia berkait juga. So dalam part D, the same batch reactor used in part C was cooled to 280 Kelvin. Okay, soalan dia kata sekarang, kita masih guna batch reactor yang sama, tetapi batch reactor ni kita dah sejukkan kepada 280 Kelvin. So just now it was 350 Kelvin. Okay, tapi sekarang reaktor tu saya dah sejukkan, saya dah guna, bukanlah saya sejukkan reaktor tu. Reaktor saya tu daripada tadi 350, sekarang saya hanya guna pada 280 Kelvin. So they say calculate the new reaction time and discuss the effect of cooling down towards the reaction time if the same conversion were achieved here. So dia tanya sekarang, dia suruh kita kira balik reaction time. Okay, kenapa dia suruh kita kira balik new reaction time? So maybe you might wonder, kenapa bila reactor tu disejukkan, kenapa reaction time kena kira balik? Sebab dia kata suruh kira kan, dia ask you to calculate the new reaction time. So why do we need to calculate the new reaction time when I cool down the reactor? Okay, let's say kamu tak pasti, just refer back untuk part C. Kalau kamu tengok part C, kita dah derive kan equation untuk cari reaction time. So apa yang berbeza dalam reaction time kalau kita sejukkan? So you can see dalam equation tu ada 3 unknown, X, K dengan Ca0. So kamu tahu conversion takkan berubah disebabkan suhu. Ca0 pun tak berubah. So Ca0 is the initial concentration, takkan berubah. The thing that changes is actually your value of your K. So your K now sekarang, you know right, kalau saya cool down ataupun bila suhu tindak balas saya berubah, K will change. So because K change, that's why your reaction time will also change. Okay, so again, Sebab kita nak maintain, okay, sebelum saya lupa, bila ada perubahan suhu, memanglah conversion tu akan berubah. Okay, maksudnya sekarang soalan ni, dia nak tahu kalau kita nak maintain conversion yang sama, okay, bila kita sejukkan dia, sebab tu reaction time tu akan berubah. Okay, so again I repeat, sebab just now I give a wrong statement, I say conversion tak berubah. Conversion akan berubah dengan suhu, for sure. Okay, so that's why dalam soalan ni dikata, dia suruh kita kira new reaction time. If the same conversion were achieved. Maksudnya sekarang saya tu sejukkan suhu, tapi saya masih nak capai conversion yang sama. So berapakah masa tindak balas yang baru? Okay, again I repeat, they want us to find the new reaction time if I want to achieve the same conversion. Okay, so that's why the reaction time will change because our value of K dah berubah because the temperature dah berubah. Okay, then subsequently dia kata discuss the effect of cooling down towards the reaction time. So kata lepas kita dah kira reaction time yang baru, kita kena discuss apa effect dia apabila kita kurangkan suhu towards the reaction time. Okay, so before we go to that, we calculate first the reaction time. Okay, so what changes in the equation from part C to part D is just the change of the K. So previously the K is at 350, now you have to calculate the K at 280. Okay, so you have to recalculate back your K at 280. Okay, so sometimes in this question, mungkin kamu confused sebab kamu sekarang ada banyak combination K. Sebab dalam soalan awal tadi dia bagi K at 300 Kelvin, right? 0.7. So kamu ada combination K1, T1, K at 300 sama dengan 0.7. You also ada K yang kamu kira tadi, K at 350, which is 2.32. Kamu ada dua combination kedua pula, K at 350, 2.32. Sekarang dia nak kira K at 280. So kamu mungkin confused nak guna K yang kat 300 ke nak guna K at 350. Actually, either one combination kamu guna pun tak apa. Means katakan kamu nak guna K at K 0.7 at 300 untuk kira K at 280. Okay. Ataupun kamu nak guna K 2.32 at 350 Kelvin untuk kira K at 280 pun boleh. Any one combination, you will still get the same K at 280 provided your calculation is correct. Okay, so again saya repeat sebab mungkin kamu akan confused. Biasa kamu ada K1 T1, kamu kira K2 T2. Soalan ni kamu ada K1 T1, K2 T2, sekarang kamu nak kira K3 T3 kan? So when you calculate the K3 T3, you can use K1 T1 ataupun K2 T2 pun tak apa, you still get the same K3. Kenapa? Sebab activation energy tak berubah. So again I have to repeat. Okay, ni pun kamu kena faham konsep dia. Konsep K, konsep A, konsep EA. Okay, A saya tak nak cakap lah sebab A tak ada dalam soalan ni, saya tak nak kamu confused. We talk about K and EA. Okay, so kamu kena ingat K, okay, berubah. Katakan kamu ada satu tindak balas. Okay, nilai K tu berubah untuk tindak balas tu bila kamu tukar suhu. Okay, so that's K. EA, activation energy. Activation energy ni adalah sama untuk tindak balas itu regardless suhu apa pun. Regardless apa-apa suhu pun, activation energy tu masih sama. So, bila kamu kira K at 300, K at 350, K at 280, activation energy masih sama. Okay, so that's why we still use the same EA that is given in the very first part of the question. Sebab tu kamu kena betul-betul faham konsep ini yang sometimes I think student can get confused. Kenapa K berubah, EA tak berubah, kenapa ni? So kamu kena faham K tu berubah disebabkan suhu. Okay, untuk tindak balas itu, tetapi EA is activation energy that is needed for the reaction to occur. So minimum energy needed. So regardless temperature apa yang kamu jalankan tindak balas tu, minimum energy yang diperlukan itu, activation energy itu adalah masih sama. That's why we still use the 5 kilocalorie per mole. Okay, so in this example, saya guna yang K pada 350. Katakan kamu nak guna K pada 300 pun, trust me, you will still get the same K at 280, which is 0.38. Alright, so you will get the same 0.38. Okay, kamu takkan dapat lari. Kamu guna mana-mana combination pun, if you calculate correctly, K at 280 is 0.38. So you will replace the K with 0.38. CA0 masih sama, X masih sama. So just because your temperature change, your K value change, your reaction time pun akan berubah and you will get 48.58 minit. Okay, so sekarang kamu dah tahu bila saya kurangkan suhu to 280, the time needed is almost is 48.58 minit. So kamu jangan lupa, dia suruh kamu, the second part of the question, dia suruh kamu discuss the effect of cooling down towards the reaction time. So apa kita boleh conclude? Kita boleh conclude, when I lower down temperature, the reaction time will be longer. Okay, so the reaction time increase with cooling down. Sebab tu kamu realize kenapa certain reaction we will use high temperature. So kenapa kita guna high temperature? Is sebab high temperature value K akan meningkat, reaction time akan menjadi lebih singkat. Okay, kalau kamu tak nampak correlation dia, okay, kamu tengok equation ni, kamu nampak reaction time dengan value K adalah berkadar songsang. Reciprocal, meaning value K untuk naik reaction time lebih tinggi, value K kena lebih rendah. Ataupun terbalik. Kalau saya nak kurangkan reaction time ataupun saya nak singkatkan reaction time, kita selalu nak reaction yang lebih singkat kan, lebih cepat. So kalau saya nak singkatkan reaction time, I want to lessen my reaction time, my value of K must increase. Dia berkadar songsang. So reaction time berkurangan, nilai K kena meningkat. Kamu kena ingat, kalau daripada Arrhenius, K akan meningkat dengan suhu kan? K meningkat dengan suhu. So kalau saya naik suhu, K meningkat, reaction time akan menjadi lebih singkat. Okay, so that's the correlation. So that's why always in reaction, kita try untuk guna temperature yang lebih tinggi. Okay, sebab reaction temperature lebih tinggi, nilai K naik, reaction time akan menurun sebab dia berkadar songsang based on this equation. Okay, so that's the correlation for you to better understand why sometimes in reaction we use a higher temperature, because we can actually reduce the reaction time. Alright, so we are done for question number 1. Okay, so question 1 takes almost 1 hour and a half sebab it's quite a long question. So I will straight away go to question number 2. I think question number part C and D is not that complicated. I think you are able to understand and you will be able to do it on your own later. Okay, so let me try to finish one question some more. Okay, question number 2 tak panjang sangat, should be okay. Right. So question number 2, the liquid phase reaction. So again, this is liquid phase reaction. So saya start dulu dengan liquid phase. Nanti kemudian baru kita pergi kepada gas phase. Okay, so liquid phase. Second, follows elementary rate law. So again, saya baik hati, saya guna juga elementary rate law. So kamu kena ingat kan dalam soalan tak semestinya semua elementary rate law kan. Kalau non-elementary, the information has to be given to you. Reaction order, kalau dia non-elementary, reaction order tu dah tak ikut stoichiometric coefficient. The information has to be provided to you. Okay, so but this is elementary, so senang lah. Okay, so kalau kamu dah tengok elementary rate law, kamu dah boleh terus derive dia punya rate law. So rate law dia minus RA equals to K. Okay, ikut reactant dalam persamaan ni A and B. So CA, CB, power of 1 for A, power of 1 of B, because in the chemical reaction, the stoichiometric coefficient for A is 1, the stoichiometric coefficient for B is also 1. So minus RA equals to K, CA, CB. Right, so done. Okay, so next, kamu dah derive rate law dia. Next, the initial concentration of reactant A is 3 mole per dm cube. So by now you should know, ini masuk dia CA0. So CA0 3. So kamu tulis CA0 3 mole per dm cube. Right, next information. And the molar feed rate of reactant B is 5 times of that of A. So again, I repeat, this is quite a new statement yang mungkin kamu tak pernah dengar ataupun we don't really encounter before. Molar feed rate, molar flow rate lah, maksudnya initial molar flow rate lah. Dia kata initial molar flow rate reactant B, so FB0. So molar feed rate of reactant B, FB0 is 5 times of A. Maksudnya molar flow rate B initially FB0 bersamaan dengan 5 FA0. Okay, so FB0 initial molar feed rate. Molar feed rate itu initial molar flow rate lah kan. So FB0 sama dengan 5 kali ganda molar feed rate of A. So FB0 sama dengan 5 FA0. So kamu tengok daripada satu ayat tu, macam mana kita nak derive information tu dalam bentuk simbol. So FB0 sama dengan 5 kali ganda FA0. Done. Okay, next. The reaction rate constant of the reaction is 2 dm³ per mole hour. So they give us the value of K. Tapi kalau kamu perasan, dia tak kata K ni pada suhu apa. So you can safely assume K yang diberi adalah pada suhu tindak balas. Okay, so dalam soalan dia tak kata K itu pada suhu apa. Tetapi, hence in this case, you may assume K yang diberi adalah pada suhu tindak balas itu. Means, kamu dah tak payah cari dah nilai K yang lain ataupun nilai K yang baru. This K can be used in your calculation. Okay, so it's 2. Next, dia kata, given molecular weight of C as 60 gram per mole. So, dia beri kamu molecular weight, which is a bit weird. Okay, mungkin, of course, kita akan guna kemudian, tapi kita ambil dulu information tu, dia beri kita molecular weight of C. So kamu tahu kan, molecular weight dia adalah sebenarnya unit dia adalah kamu tahulah gram per mole. So ataupun erti kata lain, if you realize kamu pernah baca dalam CPP, molecular weight is also a conversion factor sebab dia boleh convert daripada gram ke mole atau mole kepada gram. Okay, so again, molecular weight is also a powerful information because the molar flow rate, molecular weight is also an important conversion factor sebab molecular weight can be used to convert from gram to mole or mole to gram. Okay, tapi tu kita akan fikir kemudian lah macam mana kita nak gunakan. Okay, so let us go to the question. So dia kata soalan dia, determine the conversion if you were to produce 5 million gram per year of product C in a 5 dm³ isothermal continuous stir tank reactor. So, soalan ni kata, dia suruh kita cari X, conversion kan, X. Kalau kita nak hasilkan, if we want to produce 5 million gram per year of product C, okay, in a 5 dm³ isothermal CSTR. So dalam ni ada 3 benda. Okay, first dia nak kita cari X. So you know what we want to find X. Next dia kata, they give us 5 million gram per year of product C. So katakan kamu tak sure apa itu information tu. Okay, so again, tengok unit. Unit adalah gram per year. Gram dimension dia mass. Kan gram tu adalah mass. Year is time. Okay, year tu adalah masa. So mass per time is actually mass flow rate. So dalam soalan ni, dia beri kita information dalam bentuk yang lain. Dia beri kita mass flow rate of C. So they give us actually mass flow rate, kita guna M sebenarnya. Normally we use M to indicate mass flow rate. So it's actually MC. So ada subscript C sebab dia adalah mass flow rate of C, which is 5 million gram per year. So 5 million tu adalah times 10 power of 6. So I know now mass flow rate of C is 5 million gram per year. Okay, next. They give us volume of your reactor. Volume CSTR adalah 5 dm³. So now they give us volume reactor. Dia beri kita mass flow rate of C. So you might wonder kenapalah kita diberi mass flow rate. Tak apa, kita pergi kemudian. You process first the information. Kita ada mass flow rate. Sebelum ni kita belajar molar flow rate. Kita belajar volumetric flow rate. Now they give you another information which is the mass flow rate of C. Okay, next one dia kata the plant operates 12 hours per day, 25 days per month for 11 months in a year. Okay, so dia beritahu kita pula limitation terhadap masa operation of our plant. So our plant is only every day dia hanya kerja 12 jam, setiap bulan hanya 25 hari and every year they only work for 11 months. So information ni pun kita faham apa limitation the time of our plant. Okay, so done. Right, so macam nak solve problem ni kan. So you always ask, macam mana kita nak solve problem ni? Okay, alright. So kamu ingat, okay, this one is definitely chapter 4 kan. So kalau notes daripada, kalau dia adalah chapter 4, kita mesti akan sentiasa start from the design equation. Dia mesti kena sentiasa bermula daripada design equation untuk kita nak solve benda ni. Alright, okay. Kenapa pula? Mungkin kamu terfikir pula, kenapa design equation? Sebab kalau kamu perasan, in the question, they do give us the volume of the CSTR. Kan design equation kita kan ada volume. Design equation kita is actually to find volume. So kita tahu dia dah beri volume. Salah satu equation yang berkaitan dengan volume is actually the design equation. Tetapi you have to be very careful pula. Again, you have to check. Design equation untuk volume ada berubah, ada berlainan, depends on the three condition that I told you, which is first, dia mesti CSTR. Second, it must be liquid. Third, it must be rate law dia minus RA KCA CB. So you must find daripada notes kamu which equation that fulfill these three condition, and there's only one equation which now I've already written in the red one. I already bolded. Equation tu diberi sebagai FA0 X. Bottom KCA0 in bracket 1 minus X, CA0 in bracket theta B minus X. So kamu kena berhati-hati. Kalau dia mesti equation ni is to fulfill that three requirement. Dia mesti liquid, CSTR, rate law, minus RA equals to KCACB. So sekarang katakanlah kamu dah ada equation ni, kamu dah terfikirkan macam mana kita nak solve. Okay, ingat, come back to question. Question nak kita cari conversion. Maksudnya dalam equation ni, sebelah kiri volume kita kena ganti dengan nilai. Okay, FA0 kita kena ganti dengan nilai, K ganti dengan nilai, CA0 ganti dengan nilai, theta B pun kena ganti dengan nilai. Yang tinggal hanya X. Sebab X tu yang kita nak cari. So the rest of the unknown, selagi kamu tak boleh solve, kami memang tak boleh solve soalan itu. So you have to solve one by one, and then baru you solve the entire equation. Okay, so then now kamu tengok balik. Okay, apa yang kita perlu tahu? Okay, so first of all, volume CSTR. Sebelah kiri volume CSTR. So kamu tengok balik information yang kamu dah proses. Adakah kita diberi volume? So VI given the volume. So the volume is 5 dm cube. So belah kiri volume reactor saya dah tahu 5 dm cube. So belah kiri saya dah solve. I already solve the unknown for the left hand side. Okay, what about my right hand side? So my right hand side kita tengok one by one. Okay, so FA0. Next one, cabaran yang next one, FA0. Okay, so kita tahu FA0 tu apa? Initial molar flow rate of A, FA0. Okay, so kalau kamu perasan dalam soalan, memang tak ada sebarang information dalam bentuk mole per time. Molar flow rate kan mesti mole per time, right? So kalau kamu perasan, tak ada satu information pasal mole per time. Okay, so kalau kamu cari concentration mole per dm cube, tak boleh. FA0 mesti mole per time. So yang 3 ni tak boleh digunakan. The dm cube mole per hour 2 ni adalah nilai K. Tak boleh juga. Still no mole per time. So if you realize, the only information that somewhat related is the mass flow rate yang 5 million ni. Tetapi mungkin kamu kata mana ada kaitan tu mass flow rate, right? Okay, but this is the mass flow rate of C. So dia macam jauh kan, saya nak cari FA0. Tetapi the information given is my mass flow rate of C, MC. However, if you realize, so this is perhaps a little bit harder part. If you realize this MC, the mass flow rate, we can actually convert to molar flow rate for C because we know the molecular weight. Remember I told you molecular weight is a conversion factor to convert from mass to mole or mole to mass. So now if I have mass flow rate, if I use the molecular weight which is given, I will be able to change mass flow rate of C to molar flow rate of C. So instead of MC, I will get FC if I use the molecular weight. Okay, so maybe you ask again. However, mungkin kamu akan tanya saya, tetapi dalam soalan adalah FA0 yang kita tahu, dan tadi saya cakap tu FC kan, macam mana pula? Apa pula berkaitan FC dengan FA0? Part ni you have to then kamu pergi pada chapter 3. Chapter 3 kan kamu ingat I taught you the stoichiometric table. Kamu pun pernah buat test 1 kan, stoichiometric table. Stoichiometric table kan give you a correlation between FC dengan FE0. Maksudnya dalam kamu tengok the stoichiometric table, okay, you will have the correlation between FC dengan FE0. Maksudnya kalau saya dah dapat solve FC, if I can solve my FC, I can actually find my FA0. However, tak apa. I will solve first, cari dulu FC. Kita cari FC, baru kita fikir the next step. Okay, so now kita cari dulu berapakah, how do we get FC? Okay, so as I told you, FC, molar flow rate of C, can be obtained if we convert our mass flow rate to molar flow rate. So by right, kalau you remember, if I want to convert mass flow rate, molar mass flow rate to molar flow rate, I have to divide my mass flow rate with molecular weight. However, katakanlah you are not too sure nak tukar mass flow rate kepada molar flow rate, you are not too sure whether nak kena divide ke nak kena multiply. Okay, if you are not too sure, how do we do it? Okay, you have learned this in CPP. You just use the cancellation method. Okay, unit cancellation method. What does that mean? Okay, so of course you will start with the mass flow rate of C, the 5 million gram per year. Kita akan mula dengan mass flow rate C, 5 million gram per year. So kamu tahu, you know that your ultimate goal, dia mesti dalam bentuk mole per time kan? Sekarang kamu mass per time. Your ultimate goal is mole per time, molar flow rate. So you know, molecular weight, dia punya formula or the answer, the unit given is 60 gram per mole. Molecular weight, dia mesti gram per mole. Okay, so if I want to cancel my gram, technically the molecular weight punya gram mesti di bawah, mole di atas, baru I can cancel my gram. Or else if saya letak gram di atas, gram saya takkan di-cancelkan. If I cannot cancel my gram, I cannot get my mole. So you can see here, I can cancel my gram, I will get my mole at the top. So kalau gramnya di bawah, if the gram is at the bottom, the number follows the gram. Molecular weight tu the molecular weight 60, right? The number follows the gram. So if the gram at the bottom, the number also will be at the bottom. Sebab molecular weight dia kan 60 gram per mole. Now that you decide the gram at the bottom, hence the number will be at bottom as well. So you become multiply with 60 gram, bukan multiply, actually it's technically it's dividing by 60 gram per mole. So when you do this, you can cancel your gram. You can see now you're left with mole. So gram tu, let's say now I cancel my gram. So I cancel gram. So now I'm left with mole. Okay, dah dapat mole. So maknanya your ultimate goal nak molar flow rate kan? So mole tu dah dapat. Okay, what about the time? So now your unit is mole per year. Your unit time is now year. So now what about it? Should we do something about the unit of time? Okay, so you have to check from the question. If you realize, okay, information for time, there's only one time dia muncul, which is here. This says that the value of K is 2 dm cube per mole hour. Okay, so you can see now, you got two choice. Okay, dia ada dua choice. Satu choice is, kamu, you know in calculation, unit time tu kamu kena standardize kan? So it's up to you. Kamu nak maintain year ke, kamu nak maintain hour? So what's the difference? If you want to maintain year, let's say kamu nak guna year in your time calculation, so dalam value K ni kamu dah kena convert hour to year. Or what I do is, I will stick with hour. So my year tu saya convert kepada hour. Okay, so again I repeat, you have two options. Sebab sekarang kamu nampak unit time tu muncul pada dua nilai yang berlainan, pada dua unit yang berlainan. One is using hour, one is using year. So either you convert your unit hour in your K to year, or in my case, I convert my year in my mass flow rate tu, yang nilai year tu, I convert to hour straight away. So if I choose that, so saya kena convert lah the year to hour. However, to convert the year to hour is not straightforward sebab your plant has time limitation. Because the plan stated in the question, for every 1 year, your plan only operate 11 months. So conversion factor ubah dulu daripada year to month. Sebab 1 year kamu tak boleh assume 12 month. Because in this case, in my plan, every year the plan only works 11 month. So now I convert first from year to month. So sekarang tak capai lagi. Kita nak hour kan, kita baru capai year. Kita baru capai month. Okay, now I want to convert pula month to hour. However, I cannot straight away convert month to hour because another limitation. For every month of my plan, it only operates 25 days. So, saya kena convert dulu daripada tadi year to month, now month to day. So, you must understand kenapa kena buat stages, kenapa tak boleh sekaligus. Sebab my plan tu conversion, dia ada limitation of the time. 1 year, they only work 11 months. 1 month, only 25 days. So, now my time is now in days. Belum habis lagi sebab I want in hour. And then tambah satu lagi limitation. For every 1 day, my plan only operate 12 hours. So tambah satu lagi conversion factor because for every 1 day, the plan only works 12 hours. Okay, so now only you can see that, okay, saya dah boleh cancel year, month, day, already cancel. I'm left with hour for my time and my mole masih ada lah. Alright, so don't forget you have to solve this, okay. Then only you get the molar flow rate of C. Tapi belum habis lagi. Kami ingatkan ni baru FC. Tetapi come back to the question, kita nak cari FA0. Soalan tu kata dalam equation saya kena ganti FA0. Tapi sekarang saya hanya ada FC. Okay, so that's why I told you have to go back to chapter 3. You have to check. There is a correlation between FC dengan FA0. It states that in chapter 3 dalam stoichiometric table, FC equals to C per A FA0 X. So again, if you are not too sure, I can really understand sebab bila nak buat chapter 4 tapi kena tengok balik chapter 3, kena tengok balik chapter 2. So that's the challenges. Okay, so but if you realize soalan dalam test saya sebenarnya daripada tutorial. If you understand the concept, sebab tu soalan tutorial saya susah. Sebab I want you to familiarize already with the question of the same level in your test and final exam. So kalau kamu faham soalan tutorial ni, memang takkan ada masalah untuk test dengan final exam. Which I think you can see in test 1. Kalau boleh buat tutorial, memang test 1 tu kamu boleh buat sebenarnya if you understand. Right? Okay, so come back to this. Right, so dalam stoichiometric table, the correlation state FC equals to C per A FA0 X. So nampak sini saya dah tahu FC kan? Okay, so by right saya boleh dapat FA0. Okay, tetapi, okay, there's one interesting thing. If you perasan, okay, but before I go there, C per A ni adalah stoichiometric coefficient. Okay, so C per A ni, if you look from the equation, it will be 2/1. The stoichiometric coefficient for C is 2, for A is 1. So C per A tu jadi 2 lah. So FC sama dengan 2FA0 X. Okay, so this part you have to be a little bit, kena faham sikit. Okay. Dalam soalan, dalam equation asal, I told you yang sebenarnya kita nak cari FA0 kan? Kita cari FA0. Okay, so we find that there is a correlation. Kita tahu that FC ni sama dengan 2FA0 X. So you have two option. Okay, salah satu option adalah instead of saya hanya cari FA0, saya boleh terus cari FA0 X. Maksudnya sekarang FA0 X is my FA0 X is equal to FC over 2. So kamu boleh juga buat, okay, mungkin kamu confused tadi doktor kata nak cari FA0, kenapa sekarang FA0 X? Kalau kamu nak buat juga sebagai FA0 boleh, means FA0 equals to FC per 2X. Again, I repeat, you can also put FA0 equals to FC per 2X. However, kenapa saya tak buat macam tu? Sebab kalau kamu letak FA0 per FC per 2X, samalah juga. Okay, katakan ni kamu ganti dengan FC per 2X, darab dengan X dapat juga FC per 2, right? So, that's why instead of 2 kali jalan kerja, okay, again, if you don't understand, you can also write like this. Okay, kamu boleh juga sebagai macam ni. Okay, maknanya purely cari FC. Purely cari FA0. So kita dapat FC per 2x. Okay, so kamu ganti ni dalam equation yang atas, FA0 ni. Kamu perasan X dengan X terbatal juga. So kalau F dengan X terbatal sebenarnya sama dengan FC per 2. So instead of writing sebagai FA0 sama dengan FC per FA0 sama dengan FC per 2x, saya terus tulis FA0x. Saya terus gantikan FA0x tu sama dengan FC per 2. So saya skip satu jalan kerja. Sikit you got confused sebab saya kata dia cari FA0. Tapi kenapa terjadi FA0x? Sebab kalau tak ganti FA0x pun lalas terbatal juga X itu. Ataupun basically the top of the equation akan menjadi number. So the FA0x is now equals to FC divided by 2. Kamu tengok equation ni. FC sama dengan 2 FA0x. Hence, FA0x equals to FC over 2. So the FC that you calculated just now, 25.25. Okay, you divide by 2. Okay, you will get FA0x as 12.63. Again, I repeat. Kamu bukan dapat FA0. Kamu dapat FA0x 12.63. Okay, so again, kamu dah tahu FA0x tu 12.63. So bahagian atas ni dah menjadi 12.63. FA0x bukan FA0. Sebab setiap semester there are students who will do it again. Lepas tu dia terlupa part ni. Okay, so please understand that daripada correlation tu kita terus ganti FA0x with 12.63. At the bottom, okay, the K we are given 2. CA0 we are given 3. The X kita kena cari. Remember again we have to find the X, right? So kita kena ganti. Okay, let me explain pula part untuk theta B. Sebab equation dia kata CA0 3. Okay, lagi sekali CA0 muncul kan? So twice, that's why CA0 power of 2. Okay, 1 minus X kita biarkan. Here we can see there's a theta B. So how to find theta B? I didn't explain yet how to find theta B. Okay, dalam soalan kalau kamu remember, information dia kata molar feed rate of reactant B is 5 times of A. Or just now I explained, this means FB0 tu sama dengan 5 FA0. Arti kata yang senang, initial molar flow rate of B is adalah 5 kali ganda initial molar flow rate of A. That's why FB0 equals to 5 FA0. From this information, by right, you can find theta B because theta B equals to initial molar flow rate of B over initial molar flow rate of A. So you will do FB0 per FA0. So you get your theta B as 5. So again, FB0 sama dengan 5 FA0. Hence, FB0 per FA0 equals to 5. So my theta B is now 5. Okay, so you will replace theta B as 5. Again, this is actually quadratic equation. So CSTR akan ada banyak quadratic equation by right. So again, please try to solve this quadratic equation. And similarly, you will get two value of x of which only one x is less than 1. So you will choose that x as your answer. So the answer will be, the x will be 0.9652. So this is considerably high conversion for this question. Alright, so question ni memang a bit difficult sebab kalau kamu understand, it's not straightforward. So kamu kena betul faham a little bit of how the mass flow rate converted to molar flow rate. And then molar flow rate tu pun bukan boleh digunakan straight away sebab molar flow rate given is for product C. However, in equation dia nak cari molar flow rate of A. So kamu kena faham correlation from chapter 3, stoichiometric table, what's the correlation, then you will get the FA0x. Then you replace, then only you can solve. Okay, so for question number 2, I left with one part. Okay, I try to finish. Boleh je, I will finish in 10 minutes. Sikit je lagi. Alright, so the next part. Determine the volume of PFR to achieve the same conversion as determined in part A above. Okay, so tadi in question A, they give us volume CSTR. They ask to find the conversion in the CSTR. Part B pula, they ask us to find the volume of PFR. So terbalik, tadi give you volume, find the conversion in a CSTR. Part B, I tukar reactor, I give you the conversion sebab dia kata achieve same conversion in part A. So conversion tadi yang you calculated in part A, the CSTR, the 0.9652, you will use in this equation, and instead you have to find the volume of the PFR. Okay, so terbalik je. Okay, so similarly, what you do is, okay, you have to find the equation. So now kita dah tukar reactor. It's changed to PFR, liquid phase, rate law minus RA KCACB. So if you realize, there's only one equation that fulfills this requirement. Satu saja equation. So you check back, equation 2 adalah given as FA0. KCA0 square in bracket 1 per theta B minus 1 ln theta B minus X per theta B in bracket 1 minus X. So this is among the longest equation. So kamu dah kena cari equation mana yang nak digunakan. So that's one challenge. Find first the equation. Second challenge, nak ganti dengan nilai. Kamu kena tahulah apa yang kita nak cari. Kita nak cari volume of the PFR, meaning left hand side is what I want to find. Right hand side, everything must be replaced with numbers. So again, we do one by one. Okay, so first FA0. Okay, so part ni pun ada little bit confusion. Kenapa? Okay, sekarang kita nak kena ganti FA0 kan? Okay, so kamu kena ingat. Okay, tadi kita dah sebenarnya cari FA0X. Ingat daripada part 1 I explain to you from the correlation. Daripada mass flow rate C, from mass flow rate C, MC, I get FC. From FC, I will get FA0X. So happen, equation kita memang di atas adalah FA0X. So I will replace straight away with the numbers. However, in the part number 2, dia nak kita ganti FA0. No more FA0X. So how do we do this? Okay, so we know FA0X equals to 12.63. Okay, FA0X from part 1. Okay, so since we already know the X kan kita dah tahu sebab dia kata dalam part 2, we use the same conversion in part 1. In part 1, we calculated the X as 0.9652. So the X now, I can replace with 0.9652. So FA0X equal to 12.63 upon part A. Hence, FA0 akan sama dengan FA0 equal to 12.63 divided by X. So the X, I know 0.9652. I will get now my FA0. Okay, again, I repeat. Pada part A, we get FA0X sebab we do not know the X. In part B, now I can already find my FA0 because saya dah tahu the X. So I replace the X with 0.9652. I get purely my FA0 as 13.09. So I replace my X, I replace my FA0 13.09. Still the same K, still the same CA0, still the same theta B yang 5 that calculated just now, which I explained. The theta B is 5. So you replace everything. X also we know 0.9652. So you will get the volume of the PFR as 0.5711. Okay, so again, I repeat. What's the difference? Question 1, they ask you to find the conversion. They give you the volume of CSTR. Part B, they give you the conversion of the PFR. They ask you to find the volume. Okay, sebab tu a little bit of confusion yang pasal FA0X. Kenapa tadi guna FA0X? Sebab tadi kita tak tahu X. Kita guna FA0X. Dalam part kedua ni, kita dah tahu X. So we can already find the FA0. Okay, so and the last one for today, okay, quite simple. Dia kata, determine the conversion when the above reaction is conducted in a batch reactor with a reaction time of 0.1 hour. Okay, so dia kata now, again, we have to find conversion, but it is now a batch reactor. Okay, so again, kamu kena check. Kalau batch reactor memang dia akan, the equation is to find reaction time. So you go and check. Kalau batch reactor, liquid phase, rate law minus RAKCACB, your equation to find the reaction time is equals to the one in the rate. Kalau kamu tengok macam hampir sama dengan PFR tapi tak sama, looks similar but it's not the same. Sebab PFR is to find the volume, for the batch reactor is to find the reaction time. Okay, so the equation is in the red font. All right, so again, case ni, they give us reaction time 0.1 hour, meaning left hand side 0.1 hour. Right hand side, X tu kita nak cari, the rest must be replaced with numbers, meaning you replace K, you replace CA0, you replace your theta B, you will be able to get your X. So again, for this question as well, when you have extra time, please try to practice by yourself because this is not a straightforward mathematical equation. Kamu tengok ada ln, ada bracket, ada sub bracket in order for you to find the X. But if you solve correctly, you will get the conversion as 0.9261. Maksudnya, to achieve, when you have a batch reactor of a reaction time 0.1 hour, the conversion that you will achieve is 92.61%. Okay, so I'm done for question number 1. Number 2, you can see I go very slow and I can admit the questions are quite tough as I told you. Kenapa? Sebab I want to make sure if you understand question in tutorial, dia adalah akan sama level dengan test and exam or somewhat takkan soalan yang sama macam you can see, but the level understanding tu dah sama. If you can understand tutorial question, memang dah tak ada masalah dalam test and exam. Just that challenge dia nak solve the tutorial question. Alright. So I will finish for today. As I told you, dah lecture sekarang dah bukan 3 jam. It's only 2 hours. It's shortened down to 2 hours already. So I will see you on Wednesday. So Wednesday we will continue tutorial. Sebab tak habis lagi. Wednesday I will still continue with your tutorial. Right? So that's all for today. Hope you have a good buka puasa in less than 1 hour time. And that's all for today. Thank you everyone. So last week we have already completed question number 1 and question number 2. So as you can remember from the previous class, the question in chapter 4 is complicated. You can see that the solutions are very long, as well as I think the challenges is actually understanding the question and the information before you can actually solve the problem given. So you can see that the questions are not straightforward. You might have to do a little bit of thinking to know what is needed to solve in order to address the question given. Okay, so we will continue with question number 3. So let me try to explain it slowly, question by question. So first, they say the following gas phase reaction is carried out isothermally with no pressure drop. Okay, so the very first important information from the very first sentence is that this is a gas phase reaction. So you must always remember when we have designing reactors, the phase of your reactants are very important because you remember that the equations can be different for certain types of reactor when you have different phase. So kalau if you are doing on batch reactor, then it's okay. Both phase pun equation dia adalah sama. However, when you have flow reactors, continuous reactor such as PFR, CSTR, you know that the equations are completely different when it's liquid phase or gas phase. So this case dia adalah gas phase. Okay. Then dia kata isothermally. So isothermally meaning until now in chapter 4 we learned that we are learning to design reactors of which there are no temperature changes, meaning during the reaction the inlet outlet temperature is the same. Later when we go to chapter 6, you can see the equations become different when we have temperature change. And then no pressure drop. Okay, pun tak ada pressure drop. So chapter 4 I taught you initially the design equation without pressure drop. Then subsequently later on in chapter 4 you can check that I've also touched for equation of which there are pressure drop. Okay, so you can tahu there are difference in the equation when we have no pressure drop or when there are pressure drop ataupun pressure changes lah during the reaction. In this case, there's no pressure drop, so we can discard the parts of the pressure. Okay, so the equation, the reaction is A to produce B and 2C. Okay, so The activation energy is 8.5 kilojoule per mole with pre-exponential factor of 0.485 liter per mole minute. So they give us these two information. Probably by now you're already familiar. This information is for to be applied in Arrhenius equation. Kan kita dah belajar Arrhenius equation. In this equation is the only equation that we will have these two parameter. So activation energy is your EA. Okay, so EA kilojoule per mole. As usual, we will convert into joule per mole. So 8.5 kilojoule per mole is 8,500 joule per mole. Next, pre-exponential factor is your A. Okay, you have learned A. So A 0.485. So whenever you see ada EA, ada A, it's definitely to be applied and used in the Arrhenius equation. However, in what capacity, we don't know yet. Okay, we know mesti kena guna dalam Arrhenius. Tapi untuk cari apa, we don't know yet. Right, so we just leave it as it is. Then they say, the initial concentration of pure A is given as 5 mole per liter and 40% of A was converted. Okay, so from the second sentence, okay, there are few things that we need to process. First, dia kata, initial concentration of pure A. Okay, maksudnya, in the beginning, okay, you have only one reactant. From the equation, you can see there's only one reactant. And the reactant that enters the reactor is 100% A. Means there's no other compound, no inert, no other compound, only the reactant. So, pure A means YA0 is 1. So we use YA0 to indicate Y mole fraction, A to indicate for compound A, not to indicate initial. So the initial mole fraction of A is 1. So you can see sentence there is written as pure A. How do we translate this into calculation? It indicates that the mole fraction initially of A is 100%, or in terms of fraction, we write it as 1. Okay, so kita dah tahu YA0 is 1. Then dia kata initial concentration of A, 5 mole per liter. So of course this one I think you already know how to process. It means what CA0, 5 mole per liter. And then 40% converted, X 0.4. So from one sentence, you actually can elucidate or you can extract 3 information. Pure A means YA0 1, initial concentration of A, CA0 5, 40% A converted, X 0.4. So 3 information from one sentence. And then this is the reaction is second order with respect to reactant A. So the third sentence gives us the rate law. So last Monday, when we encountered the question, both question, it was elementary rate law. In the number 3 question, this question that we're doing today, it's not elementary. That's why they give us the information for the rate law, because the reaction order does not follow the stoichiometric coefficient anymore. So kamu kena faham, kalau elementary, we look at the stoichiometric coefficient. Non-elementary, even though dia tak cakap pun non-elementary, tapi dia dah beri kamu information for the rate law. Of course, it means that it's no longer elementary. So dalam case ni, this says second order with respect to A. So you can already write down the rate law. So how do you write down? So the rate law minus RA. Rate law mesti start dengan minus RA. Okay, elementary ke non-elementary ke? It still starts dengan minus RA equals to K. Okay, so K ni memang kena ada. Elementary, non-elementary, the K is always there. And then CA power of 2. So why power of 2? Because this says reaction second order with respect to A. So since they write is second order with respect to A, so minus RA equals to K CA power of 2 to depict second order with respect to A. Okay, so that's all information yang given. So by right, when you know all this information, you can already write down apa information yang diberi daripada soalan. Okay, so now we go to the question. It says, determine the reaction temperature in Kelvin when the above reaction is conducted in a batch reactor with a reaction time of 15 minutes. So the question asks us to find temperature of the reaction. Okay, and the second information dia kata reaction is conducted in a batch reactor with a reaction time of 15 minutes. Okay, so let's say now you are not sure how to start this question sebab very rarely you are asked to find temperature kan. Mostly before this, kalau batch reactor, you are asked to find reaction time. You are asked sometimes to find conversion. So dalam soalan previously, we use the desired equation for batch reactor to find reaction time. Tapi dalam soalan ni dia beri kita reaction time and then they ask us to find temperature. So let's say you are not sure where to start. So most of the time memang that's the challenge. Kita tak tahu mana kita nak start ataupun what are actually the equation that you want to solve. Okay, so for me, I always start in any engineering question as well or any engineering problem, you always start with what do they want to find? They want to find temperature. Okay, so you learn previously daripada banyak-banyak equation yang kita belajar, there are very few equation yang melibatkan temperature. Okay, so you remember, then you have to check back pula information apa yang ada yang berkaitan dengan temperature. Okay, you know your target is temperature. Meaning dalam equation kamu tu mesti ada unknown temperature yang kamu nak solve to get temperature. Okay, then mungkin kamu terfikir, tapi equation mana? So you have to also refer information given in the question. You try to see what information yang mungkin berkaitan dengan temperature dalam satu equation. So if you realize, there's only two information yang somewhat related, which is EA and A. Sebab you remember that dalam Arrhenius equation, okay, saya bawa ke sini. If you remember dalam Arrhenius equation ni, sekejap. Okay, kalau you remember in the Arrhenius equation, okay, kita ada A, kita ada EA, and if you realize kita ada temperature, meaning dalam equation ni saya dah ada A, I already given my pre-exponential factor. I already given my EA, activation energy, and T. So T tu apa yang saya nak cari kan? So kita somewhat realize this equation might be related because I can get the temperature of what the question wants from me. Okay, then kamu kena check pula, ada tak lagi unknown lain yang kita tak tahu? Sebab you know in equation, mathematics equation, kalau nak solve equation tu hanya kena ada satu unknown sahaja. If you have more than one unknown in that equation, memang kamu tak akan dapat solve sampai bila-bila. Okay, so you check this Arrhenius. Okay, so A, EA dah tahu, temperature kita nak cari. So barat parameter lain semua dah kena tahulah. Okay, so next R. So gas constant kita tahu because gas constant is either 1.987 calorie per mole Kelvin or 8.3144 joule per mole Kelvin. So R saya dah tahu. So then I look at the left hand side. Left hand side is K. So kalau kamu perasan, in this question, kita tak ada sebarang information of K, the reaction rate constant. We were not given any information about reaction rate constant. So now become a challenge sebab walaupun saya nak cari temperature, tetapi but at the same time, there is another unknown that I still don't know. Okay, so you have learned this in CPP or in any engineering problems. Kalau satu equation ada dua unknown, maksudnya tak boleh solve kan? I told you before. So what do we do? Bila ada dua unknown, rule dia mesti ada dua equation. Satu equation, satu unknown. Kalau kamu ada dua unknown yang kamu tak tahu, maksudnya kamu kena cari satu lagi equation. You have two unknown, you have to have two equation, then only you can solve. Okay, so now it tells you the next strategy, I have to find another equation. Sebab selagi saya tak boleh solve K, saya tak akan dapat temperature. Okay, so now you have to think, apa pula the second equation that we can use to find or we can get or use lah to find K. Okay, so let's say now you are not sure yet apa pula equation nak cari K sebab cabaran dia dah tahu nak cari T. Dah tahu equation nak cari T, tapi masalahnya equation tu ada lagi satu unknown which is K that we need to find. Okay, so you come back again to the information that is given to you. Cuba cari apa lagi information yang melibatkan K. So the only information that yang I have mentioned before K is the rate law. Sebab rate law ada K kan, minus RA sama dengan KCA square. So you know that dia mesti melibatkan equation yang ada rate law. One. Second, you check back other information. Dia kata, conducted in a batch reactor with a reaction time of 15 minutes. So you have already learned before kan, kalau ada reaction time, mesti melibatkan batch reactor. Of course, it involve a design equation. Design equation mesti ada rate law. So you know the relationship, okay? Saya tahu K ada dalam rate law. Saya tahu rate law tu ada dalam design equation. And then saya diberi satu maklumat that involve the design equation because they tell us the batch reactor adalah the batch reactor reaction time is 15 minutes. So what you do, you have to go check your batch reactor punya equation. But remember I taught you, when you want to check the equation yang nak digunakan, you have to remember the three condition according to the question. So in this question, first dia kena batch reactor, okay? Second, dia adalah gas phase. So kalau batch reactor, you don't have to worry. Gas atau liquid, the equations are the same. And the third rule that you have to follow, rate law dia. You have to check rate law. So in this question, rate law dia minus RA equals to KCA power of 2. So when you check from the notes in chapter 4, there will only be one equation that fulfills this condition. As I show you in the screen, the one that I highlighted in the red, this is the only one equation di mana it gives that reaction time for batch reactor equals to 1 per kCa naught in bracket x per 1 minus x close the bracket. So this is the only one equation where dia fulfill batch, gas phase or liquid phase pun tak apa, and the rate law of minus RA equals to KCA square. You must understand, if I change reactor or I change the rate law, equation ni pun tak valid. So that's the challenge bila if you choose the wrong equation to be used, then definitely the whole thing is wrong. Okay, so from this equation, kita kena ingat balik apa yang kita nak cari. Tadi kita dah katakan, masalah kita to find the temperature because we don't have K. So from this equation, you see that the second equation yang kita dah elucidate, the second equation tu ada K. So maksudnya, by right from the second equation, I will get my K, and then for my K, I replace into the Arrhenius in order to get my temperature. Okay, so how do we solve this? So on the left hand side, reaction time is already given 15 minutes. Left hand side, okay, K is what I want to find, so I leave it. Ca0 kita dah tahu 5.0 mole per liter. X was 0.4. So again dalam equation ni, kita dah tahu segala unknown besides K. So of course you can solve your K. You will get your K as 0.0089. So dalam soalan ni dia menarik sikit sebab sebelum ni soalannya biasa kita tahu temperature, kita cari K. Soalan ni terbalik, dia suruh kita cari K dulu, then only we can find the temperature. So you can see question chapter 4 is to mimic, dia macam nak cakap, dia bukan straightforward because you have to understand senario yang berlainan di mana how the equation can be applied depending on the situation of which you have to fit the equation to the situation. So soalan 1, 2, tahu temperature, cari K. Soalan ketiga, kena cari K dulu baru tahu temperature. Okay. Now that you have already obtained the K, then you replace into the original Arrhenius equation, then you will get the value of your temperature as 255.6 Kelvin. Okay, so this is to solve for question number 1. It's not that difficult in my opinion, tetapi I can understand it is not straightforward. Maknanya soalan tak cakap kamu, soalan tak beritahu, you don't know how do I say? Dia cara penyelesaian dia tak direct. You have to somewhat integrate, you have to somewhat interpret information, determine the relevant equation, and then you have to somewhat backtrack, cari satu lagi benda sebelum kamu boleh solve the final equation. Okay, so I'm done for part A. I will go to part B. Alright, so part B soalan dia. Determine the volume of a plug flow reactor if the reaction is conducted at the same temperature as in part A above with an initial rate of 10 liter per minute. Okay, so soalan ni dia nak kita cari volume PFR. So straightforward lah soalan ni, quite straightforward sebab kamu dah tahu design equation terus akan dapat kita punya volume of plug flow reactor. Okay, so soalan ni tak susah sangat sebab direct sikit. And then dia kata reaction conducted at the same temperature in part A above. So what does this information correlates? Dia kata nak cari volume dalam soalan kedua ni, part B ni adalah is at the same temperature as part A. So kamu kena interpret sikit lah. When we're talking about temperature, apa kaitannya dengan pengiraan kita? What's the correlation between temperature to our reaction? Okay, kamu dah tahu kan the significant effect of temperature in our calculation or in the formulation is K. Maksudnya dia tak beritahu kita kalau sama temperature in part A, meaning we interpret it as we can use the same value of K. So part A tadi kita dah dapat, kita dah kira, right? We calculated the K was 0.0089. Since the temperature does not change, hence in part B, you can use the same value of K, which is 0.0089. Okay, done. Next, dia kata, initial rate of 10 liter per minute. So by now, you already know liter per minute is volume per time. Volume per time is volumetric flow rate. And this is initial volumetric flow rate. So this one, you have to be very careful sebab kamu kena ingat, for flow reactor, PFR or CSTR, okay, volumetric flow rate, inlet and outlet is no longer the same. That's a very important thing you have to remember. Initial and outlet volumetric flow rate for gas phase is no longer equal. Okay, kita dah belajar kan kenapa dia tak equal, sebab for gas, the volumetric flow rate is influenced by the reaction, influenced by temperature, temperature change and pressure change. And that we know the correlation. Okay, the equation is given as following. Kalau gas phase, flow reactor, PFR or CSTR, outlet volumetric flow rate equals to inlet volumetric flow rate in bracket 1 plus epsilon x. Technically, kalau ada temperature, ada pressure change, P per P naught. Kalau ada temperature change, T naught per T. Tapi sebab soalan ni tak ada temperature change, no pressure change or pressure drop. That's why part yang P per P naught, T naught per T tu tak ada kat bahagian belakang equation ini. Okay, done. Okay, so how do we solve this? Okay, so again, as I told you, bila kita nak guna design equation, you have to check these three information. First, plug flow reactor. Second, gas phase. So tadi kalau macam batch reactor, the phase are not important. Equation dia sama. Tapi kalau flow reactors, PFR or CSTR, you have to really check is the equation is must be for gas phase. Okay, so soalan ni adalah gas phase. So tu syarat kedua. Third rule is of course the rate law. So rate law masih sama sebab rate law is depending on the reaction. Tak bergantung kepada reaktor. Apa-apa jenis reaktor pun, rate law dia yang tadi kita deduce minus RA equals to KCA power of 2 tu, regardless whatever reactor, rate law masih sama. Okay, so if you check this equation, the equation that fulfill these three condition is only one equation yang akan fulfill. So equation dia is given in this rate the rate form that I highlighted. Okay, so kalau kamu check, sama je kalau kamu ingat equation bila saya deduce kita ada 3 version kan. Okay, the first 2 version adalah untuk cari volume PFR. The third version is to find the space-time. Then kenapa ada 2 version untuk volume tu? Because the first version, if you know FA0, inlet molar flow rate. The second version, if you know inlet volumetric flow rate. So dalam contoh soalan ni, we are given inlet volumetric flow rate. That's why I use the second version of the equation. So penting juga untuk kamu tahu beza dia dan bila kita nak guna version pertama, bila kita nak guna version kedua. Okay, so if you remember, I taught you equation dia panjang kan, banyak equation. This is the longest equation that you have to apply lah. Nasib baik kamu tak payah hafal, you just need to know how to use it. Tapi sometimes walaupun equation diberi pun, sometimes we might not be able to solve it accurately. Okay, so let us discuss macam mana kita nak solve question ni. Okay, so you know kita nak cari volume. So the left hand side is what we want to find. VPFR is the unknown we want to find. Meaning on the right hand side, everything else have to be solved and with numbers. Okay, we start first with initial volumetric flow rate. So this one kita dah tahu is 10 liter per minute given in question. Settle. K value as kita dah deduce because it's same temperature as part A. So value K dalam part A tu kita boleh guna dalam part B, which is 0.0089. Yang tadi kita kira, kita dah boleh guna. Ca0 is already given in the question, which is 5 mole per liter. So we can use it. Next, you can see X. X pun kita dah tahu, the conversion is still 0.4. Settle. And next is epsilon. So epsilon ni lah kita kena cari. Okay, so you remember kalau gas phase, flow reactor, dan ada satu tambahan parameter yang kita kena cari, which is epsilon. Okay, so kita kena ingat balik lah macam nak cari epsilon. So epsilon ni kalau kamu ingat, dia ada equation, dia ada sub-equation. So epsilon ni tak boleh cari direct. You have to somewhat find the main equation and then the sub-equation. So you don't have to memorize, tetapi you have to really understand sebab equation dia boleh berubah depending on the reaction. So what do I mean by that? Okay, epsilon, if you remember, equation dia adalah equals to YA0 sigma. Okay, nak cari epsilon, equation dia is equals to YA0 sigma. YA0, kamu tahulah kan, Y is mole fraction, A is for compound, A0 is for initial. So that's initial mole fraction of A, YA0. So just now previously kita dah deduce earlier on, they say this is pure A reactant, A enters pure A enters the reactor. So meaning YA0 is 100% initially, berapa mole persen A yang masuk adalah 100% sebab dia adalah pure A. So dalam bentuk fraction, it is 1. So YA0, 1. Dan next, sigma. So sigma pula ada lagi satu equation untuk cari sigma. That's why I said it's a equation with sub-equation because kita nak sekarang cari sigma pula. Okay, nak cari sigma, equation dia tak fix. Why do I mean by tak fix? Because if you remember, sigma is basically the addition of subtraction of your stoichiometric coefficient ratio, di mana dia boleh jadi tambah untuk produk minus untuk reactant. So you have to remember, dia hanya akan stoichiometric coefficient ratio tu will be positive for the product, negative for the reactant. Okay, so in this case, in this example, we have 3 compound A, B and C, of which A is reactant, B dan C adalah product. Okay, so that's why when we write down the sigma punya calculation, you see it become B per A, ratio of stoichiometric coefficient of B over stoichiometric coefficient of A plus C per A, stoichiometric coefficient of C over A. So kenapa it is plus for B and C? Because B and C is product. Okay, then minus 1. Technically is minus A per A sebab A adalah reactant. That's why you have to minus because A is reactant. Technically adalah minus A per A. Tapi A per A adalah 1. That's why they write it as minus 1. Okay, so if you are confused kenapa B per A, C per A, tiba-tiba 1. Sebab 1 tu sebenarnya adalah untuk A per A. So it become 1 lah. Okay, so you replace the stoichiometric coefficient accordingly, and please make sure you check sebab this part student tend to do the mistake sebab dia tak nampak ataupun dia mungkin dah confused. For in this example, the stoichiometric coefficient for C is 2. Okay, stoichiometric coefficient for A is 1, for B is 1, for C is 2. Sebab tu dia menjadi 1 plus 1 per 1, B per A is 1 per 1, plus C per A is 2 per 1, minus A per A, 1. Okay, when you calculate this, you get your epsilon as 2. So as I told you before in lecture previously, epsilon ni boleh jadi negatif, boleh jadi positif depending on the reaction. So if let's say you get negative pun tak apa, if you get positive pun tak apa, asalkan you calculate correctly. So the possibility of getting negative or positive epsilon is normal. Okay, so kalau kamu dapat negatif, kamu jangan takut kamu rasa salah. It can be negative, and if you get positive pun, it can be positive, but make sure you calculate correctly. So once you get your epsilon, okay, straightforward, you just replace into the equation. So this is quite a long equation. Okay, you have to learn when you got time after this. Please make sure you really try to practice using your calculator to calculate. You should be able to get the volume of the PFR as 330 liter. Okay, so that's all for question part B. Question part B is quite straightforward, tetapi you must really remember yang soalan 1 dengan 2 sebelum ni liquid phase. Kamu akan perasan equation dia betul-betul berlainan bila kita ada gas phase reaction. So as long as you remember that, you should be able to solve question number 3 quite smoothly. Okay, so as usual, I will leave about 1 minute for you to catch up or to just practice. If you have your calculator in front of you, I will come back in about 2 minutes time. Okay, so we will continue with the next question. Question number 4. Okay, so question number 4. Let me see. Question number 4 or question number 4. Okay, I will go to question number 4. Okay, so So as usual, I will leave some questions for you as your homework. Okay, so I will solve question number 1, 2, 3, and 4, the last one. So question 5 and 6, please, when you have time, additional time, please try to solve question number 5 and 6 by yourself. In the question that I already posted in Teams, you already have the final answer. You should be able to solve it by yourself. But if you cannot, okay, if you have tried and then you cannot solve it, you may refer to me if you have any difficulty in solving. Okay, so question 5 and 6 is your homework. Question 5 is quite straightforward. Question 6 also quite straightforward. I have covered before in our lecture. Okay, so I give you 5 and 6 as homework. I will solve question number 4, the last one for today's session. Okay, so the question says, the following liquid phase elementary reaction is carried out isothermally with no pressure drop. Okay, so question number 4, kita come back kepada liquid phase. So kamu kena faham lah, memang soalan dia, you have to really check the phase. Sebab kamu tahu significant difference dia dalam persamaan in the design equation is determined by the phase of your reactant. So dalam case ni, dia come back balik kepada liquid. Okay, so dia kata elementary reaction. Okay, so elementary balik. Soalan nombor 3 non-elementary. Soalan nombor 4 come back to elementary. So kalau elementary reaction, kamu dah boleh straight away tulis dia punya rate law. Okay, so that really helps you bila kamu dah boleh tulis rate law dia. So contoh case ni, okay, dia beritahu elementary. So rate law dia minus RA equals to K. Okay, the two reactant A and B. So CA, CB, stoichiometric coefficient in form of A is 1, stoichiometric coefficient of B is also 1, meaning first order with respect to A, first order with respect to B. So, you know kalau power of 1 is still the same, right? 4 power of 1 is still 4, 10 power of 1 is still 10. Sebab tu you can still write it as KCA, CB. Okay, so first kamu dah boleh tulis rate law. So by sekarang dah minggu 8, and I see from the test, most of you, I would say all of you are able to write down the rate law. Okay, so that's very good progress, right? So next dia kata isothermally no pressure drop. Okay, so tak payah consider pasal perubahan temperature, tak payah consider about perubahan tekanan. Okay, so nanti kamu ada masa, you must try question number 5 sebab question number 5 tu ada pressure drop. Okay, that's why I sengaja biarkan soalan nombor 5 tu sebab I want to see whether you understand apa berubah kepada equation apabila kita ada pressure drop. Okay, so question number 5, if you have time later, since I'm going to finish my class 1 hour earlier, you have free time. If you have the time, please solve question number 5 and 6 on your own. Okay, then the reaction is to produce 2C. Okay, so the reaction rate constant at 30 Celsius is 15 dm³ per mole minute with activation energy 25 kilojoule per mole. Okay, so soalan ni diberi kita value of K, tapi K ni pada 30 Celsius. Okay, so K at 30 Celsius is 15, EA 25. Okay, done. So the question says, let's go to the question. Alright, so question dia kata, determine the initial concentration of A. So dia nak apa? Dia nak kita cari CA0. Okay, so this is something different, right? Sebab soalan sebelum ni cari temperature, cari reaction time, cari volume, cari temperature. Soalan ni dah pelik sikit, cari CA0. So sebelum ni soalan kita biasa diberi CA0. Soalan ni dia suruh kita cari CA0. If the reaction is carried out in a PFR with a space velocity of 1.5 per minute at 50 Celsius with 60% conversion of A. So soalan ni kata, dia suruh kita cari CA0. Dia beritahu reaction ni dalam plug flow reactor, dalam PFR, dia beri kita space velocity PFR tu 1.5 per minute. Okay, so something different, right? Sebelum ni kita diberi volume. Soalan ni kita diberi space velocity untuk PFR ini. Okay, so that's something different. Okay, so space velocity of the PFR 1.5 per minute. So it's okay kalau at this stage, kalau kamu tak tahu macam mana nak buat pun tak apa. Tapi yang penting kamu boleh synthesize the data or the information first. So information dia, space velocity, PFR, 1.5 per minute. So next dia kata 50 Celsius. Okay, so dia kata sekarang dalam kes ni dia nak cari CA0 untuk PFR dengan space velocity 1.5 pada suhu 50 Celsius. So straight away dalam your mind, you already kena faham maksudnya jika ada sebarang pengiraan yang melibatkan K, which definitely akan ada sebab kamu tahu kita akan guna design equation. Kamu tahu design equation tu ada rate law. Dalam rate law tu ada K. So selagi ada any calculation yang melibatkan K, the K must be at 50 Celsius. Okay, so kamu dah faham kan dalam soalan ni, kita ada nilai K but the K is at 30 Celsius. So automatically kamu tahu, okay, K, walaupun saya ada K, tapi K saya bukan pada suhu tindak balas. Meaning, naturally kamu faham, saya dah kena cari K yang baru, which is K at 50 Celsius. Okay, so that's one thing. Okay, so it's up to you. Kalau macam kamu rasa benda tu something yang kamu nak solve dulu, you can always straight away solve dulu untuk K supaya kamu tak buat salah. Mungkin nanti kemudian kamu terlupa. So you can always solve first. Kamu tahu mesti ada nilai K. So kalau kamu rasa macam kamu tak nak solve kemudian, you can always solve first. You find the K at the new temperature first. Okay. So next, dia kata conversion as 0.6. So always remember, when conversion is given in percentage, you always have to convert into fraction. So X is 0.6. Okay. The reaction mixture consists of 60 mole percent B and the remaining A. So dia beri kita sekarang initial mole percent or kita boleh tukar kepada mole fraction kan. So dia beri kita initial mole fraction of B 0.6. So YB0 0.6 automatically of course lah YA0 0.4. So dia beri kita YB0 0.6, YA0 0.4. Okay, so that's the information that they give. Macam mana kita nak guna information tu, kita tunggu dulu sebab kita tak tahu macam mana dia akan digunakan. Okay, so that's all that you have so far. You already elucidate the rate law. You know this is liquid phase. You know the value of K, tapi K pada 30 Celsius. You know EA, you know YB0, you know YA0. Okay, so how do we solve this? Jadi kita nak cari CA0. Dia nak cari CA0. Okay, so if you realize from the question, okay, mana kita nak cari CA0 tu? Okay, the only information macam saya always tell you, kamu kena tahu, okay, apa information, apa benda kita nak cari, CA0, and then tengok balik apa information yang boleh digunakan ataupun apa information yang possible akan muncul dalam satu equation yang mana kita boleh cari CA0. So if you realize the only one information is actually the space velocity. Okay, dia beritahu kita space velocity of PFR 1.5 per minute. So kamu rasa macam this is something unique information kan? Biasa kalau macam soalan-soalan lain, information dia almost the same. Tapi dalam soalan ni dia tiba-tiba beri kita space velocity. So you know that somewhat mesti dia melibatkan equation yang ada space velocity. However, kamu mungkin terfikir tapi I've never taught you equation yang ada space velocity. I did taught you that space velocity sama dengan 1 per space time. Tu saya pernah ajar kamu. Space velocity sama dengan 1 per space time. Tapi saya tak pernah ajar kamu design equation yang ada space velocity, which is correct. I never teach you any design equation yang melibatkan space velocity. Tetapi if you remember, I did taught you design equation yang ada space time. Do you remember? Untuk setiap design equation yang saya ajar kamu, sebenarnya saya ada ajar version yang ada space time. Okay, ataupun erti kata lain, okay, if you remember, katakanlah kamu tak ingat juga version yang space time pun tak apa. Okay, so you go back and check your design equation. Okay, again sama, kamu kena check design equation yang fulfill 3 condition. PFR, liquid, rate law dia minus RA equals to KCACB. Kamu kena betul-betul check equation yang ada tiga condition ni. So if you check, there's only one equation ataupun by right ada 3 equation lah yang fulfill design yang fulfill that condition kan, atau you 2 version pertama yang melibatkan FA0, version kedua yang melibatkan epsilon naught, These two version is to find volume. The third version is to find space-time. Okay, so version yang kedua dan ketiga pun sebenarnya kamu boleh guna. It just depends on how you rearrange the equation. So for example dalam case ni, saya guna yang version kedua. Version kedua equation tu kata the volume of PFR untuk PFR liquid minus RA KCACB is equal to this equation. Volume PFR equals to epsilon naught, your initial volumetric flow rate, per KCA naught in bracket 1 per theta B minus 1 ln theta B minus X per theta B1 minus X. Ini version yang ada epsilon naught. Okay, so dari version ni, kalau kamu ingat, okay, again saya takut kamu confused. Dia ada dua version yang volume dengan version space-time. Version space-time pun boleh kamu terbalikkan sahaja, kamu dah dapat space velocity. Ataupun saya guna version yang ni sebab sama je konsep dia. Okay, kenapa I say it's the same? Okay, kalau kamu ingat saya kata space velocity adalah 1 per space-time. Okay, kalau space-time, it is initial space-time dia punya formula volume per initial volumetric flow rate. Kalau kamu ingat, space-time tau, volume per initial volumetric flow rate. Kalau space velocity reciprocal, maksudnya initial volumetric flow rate per volume reactor. So kalau kamu perasan pada equation ni, equation yang saya tengah highlight ni, katakan saya tutup yang bahagian depan. Let me close the front part. This one you can see clearly. Okay, ini adalah apa yang kita dapat daripada notes. So kalau kamu nampak sini, if I remain my initial volumetric flow rate kat sebelah kiri, sebelah kanan, I move my volume from left to right. So kalau saya move volume PFR saya daripada kiri ke kanan, dia akan jadi pembawah. Okay, dia jadi pembawah initial volumetric flow rate kepada volume PFR. Itu adalah space velocity. Kan saya kata kalau space time terbalik, volume per initial volumetric flow rate. Space velocity reciprocal kan. So dia jadi initial volumetric flow rate kepada volume. So sekarang belah kanan saya dah dapat space velocity. Maksudnya the other unknown tu kamu kena pindah ke sebelah kiri. So means the KCA naught, kalau saya pindah ke sebelah kiri, dia jadi pengatas. The whole entire in the bracket, the big bracket, bila dia pindah ke sebelah kiri, dia akan jadi pembawah. You know mathematics, right? Kalau pembawah pindah ke the other side, dia jadi pengatas. Yang pengatas bila move to the other side, dia jadi pembawah. So the entire big bracket will be your pembawah already. Your KCA naught is your pengatas. Okay, so now you dah basically derive the equation to find space velocity. Okay, tadi yang saya kata version yang menggunakan space-time. Okay, let me explain when showing you the notes. Kejap, let's notes chapter 4. Okay, so if you remember, saya buka notes lah. Kalau tak, saya susah sikit nak explain tanpa notes. Okay, so you remember, this is PFR, liquid phase second order. Alright, so if you remember, this was the equation yang saya cerita tadi. Yang saya katakan ada 3 version kan. Kita belajar 3 version kan. Version yang tadi saya ajar kamu untuk kita gunakan adalah version yang kedua. Volume sama dengan initial volumetric flow rate, KCA naught, the big bracket. Okay, kita guna version ni pun kita boleh cari space velocity. Version yang ketiga ni pun boleh sebab version ketiga ni adalah space time. So kami ingatkan space velocity is 1 per space time. So kalau kamu nak tukar ni untuk mencari space velocity, kamu terbalikkan sahaja. Sebab tu dia akan menjadi KCA naught ni atas, the big bracket ni bawah. Sama je dengan apa yang saya derive tadi yang saya tunjuk dalam soalan adalah the same. Either you derive from the space time or you derive from the volume, you will get the same final design equation to find the space velocity. That is what actually I wanted to tell you lah supaya kamu tak confused. So in this equation kita ganti. So the space velocity 1.5 per minute. Okay, so that's what kita nak cari CA naught kan. Jangan lupa kita nak cari CA naught. So again, segala unknown kita kena ganti dengan nilai. Hanya tinggal CA naught yang kita nak cari. Okay, so space velocity 1.5. The K, so sekarang kamu kena ingatlah, kita kena cari K pada suhu 50 Celsius. Because although we are given the value of K, the K is at 30 Celsius. However, our reaction is at 50 Celsius. You have to find the new K. So yang ni saya tak ajar dah lah, kamu dah faham kan? Kalau kita ada K1, T1, kita kena cari K2 at T2. So I have K1 0.15, K1 15 at 30 Celsius. I can find K2 at 50 Celsius. However, don't forget, the temperature must be converted into Kelvin because the value of R, regardless 1.987 or 8.3144, the temperature unit is still in Kelvin. So don't forget 50 Celsius, 30 Celsius, you must convert into Kelvin. Then only you can substitute to find the new K at 50 Celsius. Okay, so kita katakan kamu dah kira K yang baru, kamu ganti. CA0 I want to find. So the bottom sekarang kita tinggal X. X is given as 0.6. 60% kan, 60%. X is 0.6. We have theta B. So kita tak cari lagi theta B kan. Okay, so macam mana kita cari theta B? So theta B ni tak ada masalah lah. Kamu dah pernah belajar dalam test 1 pun you have already solved question. What is theta B? Theta B is the ratio of initial amount of B over initial amount of A. This amount can be concentration, molar flow rate, can be mole fraction. So in this question, we are given the initial mole fraction of A and B. Sebab dia kata mole fraction of B 0.6, 60%. Hence, mole fraction of A 0.4, 40%. So you can find theta B as equals to YB0 per YA0. So equals to 0.6 divided by 0.4, you get 1.5. So now that you have already solved your theta B, so you can replace your theta B as 1.5. You can solve to get your CA0 as 0.044 mole per dm cube. So done for question number A. This is 4A. Alright, so last one, question 4B. Okay, so last one for today. Okay, so last one, dia kata, to increase the conversion of A to 90% from part A above, a CSTR with a space velocity of 0.42 minute is used in series with the first PFR. As a result, the initial mole percent of reactant A and B must be changed. Determine the new initial mole percent of reactant A and B using the initial concentration of A and the reaction rate constant obtained in part B in part A above. Okay, I don't think I can manage to finish this question. I only left 6 minutes. I'm so sorry because the 10:30 meeting tu I cannot be late dan saya tak rasa tak sempat untuk saya habiskan, and I think it's not fair kalau saya rush soalan ni sebab kalau tak faham pun no point, right? I explain. So I'm so sorry. I will continue part B during our lecture next Monday. I just finished a little bit of this part B and then we will continue with lecture. Okay, so I'll finish the tutorial session early today. If you have time, 1 hour, can you please try to do question 5 and 6? And I promise I will come back to question 4B this Monday during our lecture. Okay, so thank you everybody and I will see you next Monday. And please don't forget your lab. Let me open up. Right, so, okay. Right, so but before I continue, let me explain a little bit lah sebab last week saya stop kat part A. For me to go for B, I have to explain again lah the question. Okay, so the question was, if you remember, we have a liquid phase reaction, elementary reaction. Okay, so we know that in 4A part, we have already elucidated or we have already came out with the rate law. So the rate law was actually minus RA equals to KCACB. Okay, so that one done. Okay, and then they give us the value of K, that's reaction rate constant, which is 15, but the 15 is actually at 30 Celsius. So you understand, if you're given the value of K at a certain temperature, you have to always check before you use it in your calculation. Sebab as I told you, fundamentals dia, the value of K for your design of reactor, the K must be at your reaction temperature. So if you have K at any other temperature besides your reaction temperature, you have to find the new K. Okay, so example in this case, your K is 15 at 30 Celsius, tapi establish kat part A ni, the reaction is at 50 Celsius. So naturally, kamu kena carilah K baru, which we already done. Okay. Lepas tu, dalam soalan part A ni, dia suruh kita cari CA0, initial concentration of A. Dia suruh kita cari CA0, if given, reaction tu dalam PFR, and space velocity of the PFR is 1.5 per minute, and dia beri kita conversion. So for A was a bit tough sebab biasanya soalan we are given all the information, we are asked to find the volume. Okay, so this case dia pelik. Okay, dia tak beri volume, dia beri kita space velocity, and they ask us to find the initial concentration of A, CA0. So this is a little bit higher level of understanding sebab in the notes, although I give you equation, kamu tahu kan, chapter 4 got a lot of equation, tapi equation untuk space velocity ni I didn't provide to you. I did teach you how to derive design equation untuk cari volume and then to cari space time. Tapi I didn't give for space velocity. Tetapi dia tak susah sangat pun because space velocity is actually 1 per space time. So formula space time tu kamu just terbalikkan, you reciprocal, meaning the top will become the bottom will become the top. You already basically get the equation to find space velocity. Okay, so dia taklah susah, tapi just that memang tak ada equation tu directly in my notes because I wanted you to tengok you faham tak apabila kita ada case di mana kita nak cari space velocity. Okay, so it's already done in part A. Dia suruh kita cari CA0, which we have already discussed. Okay, so now we go to the part B. Okay, so part B soalan dia kata pula, because the conversion in part A was only 60%. Okay, dia guna PFR, the first reactor, the conversion was 60%. So dia nak increase conversion to increase the conversion to 90%. Okay, from part A. So means reactor pertama 60%, reactor kedua I want to increase to 90%. So dia kata a CSTR with a space velocity of 0.42 per minute is used in series with the first PFR. So soalan dia pelik sikit. Dia combine reactor, tapi biasanya when I teach you, we combine identical reactor. Kita combine 2 CSTR ke, 2 PFR ke. Okay, so this one a little bit weird. They combine PFR and the first reactor was a PFR. The second one is a CSTR, which I admit practically dia tak mungkin terjadi lah. We do not mix reactor dalam tindak balas. Okay, so just take this as a scenario saja yang berlaku dalam soalan, tapi practically we do not mix the different types of reactor. Okay, so the soalan dia kata the second reactor is a CSTR and dia beri the space velocity 0.42 per minute. So kamu kena be very careful. Kalau space time, unit dia time lah, minute. Space velocity kan 1 per space time. Sebab tu unit dia pun jadi per time. Instead of time, ia jadi per time for space velocity. Okay. So dia kata, because of this, the initial mole percent of reactant A and B must be changed. Okay. So determine the new initial mole percent of reactant A and B using the initial concentration of A and the reaction rate constant obtained in part A above. Okay, so soalan ni mungkin nampak a bit confusing. Okay, dia kata sekarang, in order for us to increase the conversion to 90% dalam reaktor kedua, maksudnya sekarang the initial mole percent yang kita guna sebelum ni dah tak boleh digunakan sebab earlier on in the question part, in the earlier part of the question, dia kata that the reaction mixture consists of 60 mole percent B and the remaining A. So dia kata dapat A tadi, kalau saya nak guna hanya satu PFR, saya akan guna 60 mole percent B, 40 mole percent A. Tapi sekarang dia kata sebab kita nak sambung kepada reaktor kedua, so percentage ni dah tak boleh digunakan. Okay, so maknanya kita kena cari percentage yang baru. Means I can no longer use 60 mole percent B and 40 mole percent A. I have to change this mole percent. Kalau saya nak mencapai 90% pada reaktor kedua, Dan syarat dia space velocity untuk reaktor kedua ni, yang CSTR ni mesti 0.42 minit. Okay, so dia kata lagi, certain parameter kita boleh maintain. Means initial concentration of A kita boleh maintain. Kita boleh guna CA0 from part A. Dan dia kata reaction rate constant pun kita boleh guna part A. Means CA0, K kita maintain. Tapi kita kena cari the new mole percent of A and B. Okay, so this is a challenge. As always, engineering question, kita tak tahu macam mana nak mula, or in other words, sometimes you have idea equation mana, tapi macam mana kita nak suit equation to the question. Okay, so if it's me, okay, the easiest one, I think, in my opinion, you have to first figure out equation mana yang berkaitan. Okay, of course, it's easier for me to say lah, sebab saya tahu kan, sebab saya dah familiar soalan ni. But for reaction, okay, like for example, if you came across certain question, kamu kena really understand, okay, apa information diberi dan what are the most likely equation. So for example, dalam soalan 4B ni, you know that information yang out of norm, ataupun kalau kamu perasan dalam soalan tu, information yang biasanya tak diberi ataupun information yang kamu tak biasa jumpa tetapi ada dalam soalan ini. So biasanya maklumat yang tak biasa dijumpa inilah sebenarnya most of the time adalah key ataupun your key how you start tackling the question. So for example, in this case, it's very obvious in this question, space velocity of 0.42 per minute. So you know that this is something that is you don't normally encounter in question. So you have idea that ni mesti satu information yang berkaitan dan mesti ada equation yang berkaitan yang saya boleh gunakan. Okay, so you have to come back lah notes kepada chapter 4. You know, again, same part. I did taught you how to get the equation, but I taught you only to find volume dengan space time. However, ni adalah space velocity, tapi konsep dia masih sama. Okay, you can first find the space velocity punya formula, space time punya formula, ataupun formula volume pun boleh. Lepas tu kamu rearrange untuk mendapat formula space velocity. So for example, in this case, kamu nak cari equation pun you have to remember the three main things. The types of reactor, CSTR. You have to remember the rate law. So rate law dia minus RA equals to K CA CB. So again, saya kena emphasize, rate law dia tak berubah mengikut reactor. Rate law is mengikut tindak balas. Maksudnya kalau tindak balas sama, you run in different reactor, rate law tu masih sama. Okay, dia bukan bermaksud kalau saya tukar CSTR, rate law dia jadi minus RA KCA square. Kalau saya tukar PFR, dia jadi minus RA KCA CB. Tak. Okay, sebab kamu understand, reactor tu is just a vessel where the reaction takes place. So you letak dalam CSTR ke, dalam PFR ke, tindak balas tu masih berlaku dalam cara yang sama. That's why rate law dia will not change. Okay, so I change to CSTR ke, I change to PFR, the rate law is still minus RA equals to KCACB. That's the next one. And third, you have to check liquid phase reaction. Ketiga-tiga ni, kalau kamu tengok salah satu salah pun, you will use the wrong equation. So bayangkan kalau you use the wrong equation, kat step pertama tu kamu dah salah the entire thing. Okay, so later I will release you the marks for the test. Nanti saya release dalam e-learning, ECT. So for those who do not get good marks, don't feel demotivated. Most of the time when I do a post-mortem of your answers, most of the time sebenarnya most of you, if not I can say all of you dah faham konsep. Tapi dia mungkin terjual pada part awal tu dia punya consequences salah keseluruhannya. Walaupun mungkin dia faham konsep tu, benda tu betul. Just that you wrong at the very first part of the understanding. Okay, kamu salah process information, sebab tu menyebabkan kesemuanya salah. So if you have not so good marks, do not think that because you tak tahu buat. Sebenarnya most of you dah tahu buat. Just tersilap langkah, some of you unlucky, tersilap langkah di part awal yang menyebabkan salah keseluruhannya. Okay, so later I will release you the mark. So if you want to see the answer, you can always come back to me, check with me if you really want to see your answers. But that is one of the postmortem I found after I did and look back of all your answers. Okay, so come back to this. So why I keep emphasizing this is because the same. Kalau kamu tertengok, if you look or you check the wrong equation, then habislah keseluruhan question. So maybe like 15 marks, you wrong at the very first equation, the entire 15 marks become 0. So tak semestinya, tak bermaksud kamu tak tahu. Kamu tahu je, just that tertengok equation yang salah. Okay, so that's the consequences lah, right? So come back to this. So if you look at the correct equation, okay, ingat again, equation saya adalah hanya volume dengan space time. Nak cari space velocity, terbalikkan sahaja equation yang untuk space time, and you will see that the equation becomes like this. Okay, space velocity equals to equation dia K CA naught in bracket 1. Oh, sorry, this one saya kena ajar. Sorry, I forget. This is the second reactor. Okay, sorry ya, sebab again, I forget. Okay, yang saya ajar kamu dalam design dalam chapter 4, single reactor. I didn't teach you reactor bersiri untuk design equation. Okay, so sorry, I have to come back, I have to reverse back. Okay, saya kena ajar pula equation tu. Saya lupa sebab dalam design equation, the one that I teach you is design equation untuk single reactor. You have learned reactor in series dalam chapter 2, tapi kamu tak belajar derive design equation dia. So saya kena ajar sikit untuk derive equation dia. Okay, so it's okay, I come back how to derive the equation, right? So now kita nak derive space velocity equation untuk the second reactor in the system, which is not so straightforward. Okay, we have done one question previously, but I will just explain again. The rate law for the second reactor is still the same. Masih minus RA equals to KCA CB. Okay, tetapi now we are talking about the second reactor in series. The only difference is rate law masih sama, but the concentration now becomes the concentration of A and B in the second reactor. So kalau biasa, kalau satu reactor, we just write KCA CB. However, when you have two reactors, you have to identify, are you talking about the first reactor or you're talking about the second reactor? In our example, we are talking about the second reactor. Sebab tu kita kena tulis sebagai KCA2 CB2 to indicate concentration in the second reactor for A and for B. Okay, then you have to remember pula, we have to derive the equation for the CA2 and CB2. So sebelum ni kamu selalu buat untuk CA, CB. Apa yang berubah kalau kita nak kira concentration in the second reactor? Dia tak susah sangat. The only difference is in the first reactor kita measure in terms of X1, conversion pada reaktor pertama. Kalau reaktor kedua kita akan measure in terms of X2. Sebab tu formula dia akan menjadi for CA2 become CA0 in bracket 1 minus X2 because now we are measuring the conversion in the second reactor. So for CB as well, so become CA0 in bracket theta B minus B per A X. Okay, so B per A X. The B per A in this example is 1. So B per A tu, we look at the chemical equation. So B per A is 1. Sebab tu you become CA0 theta B minus X2. Okay, settled. Okay, now part yang how do we combine all this information? Sebab as I told you, dalam chapter 4 saya tak ajar reactor in series punya design equation. But you have learned in chapter 2 a little bit. Okay, apa maksud dia? Okay, dalam chapter 2 you have learned volume of the second CSTR, okay, kalau bersiri equals to FA0 in bracket X2 minus X1 per minus RA2. This one kamu belajar dalam chapter 2. Okay, just dalam chapter 2, kalau kamu ingat, nilai minus RA2 is given to you, kan? We have a table or we have a plot. Kamu terus tengok, kalau X2 katakan 0.8, berapa minus RA2? Kamu terus dapat nilai dia, kamu terus ganti nilai. Itu yang kamu belajar dalam chapter 2. Tapi sekarang bila di combine dengan information chapter 4, kita dah tak tahu berapa nilai minus RA2 already. Okay, in chapter 2, we are given. In chapter 4, become harder. I do not know the minus RA2 value. But instead, I have already know the rate law. So, minus RA2 equals to KCA CB2. Okay, kita dah explain. Okay, then, you know CA2, CB2 ni kita kena express in the form of CA2 is CA0 1 minus X2. CB2 is CA0 in bracket theta B minus X2, which I've already explained just now. Okay, so when we combine, kita dapat dalam bentuk ini. Okay, so kenapa CA0 square? Because CA2 ada satu CA0, CB2 pun ada satu lagi CA0. So when you multiply, you get power of 2. So it become K CA0 square. So in bracket 1 minus X2 in bracket theta B minus X2. B per A is 1. Then, okay, the part is sekarang, bila we derive this, we don't have initial volumetric flow rate, epsilon naught. Okay, sekarang kita ada FA0 di atas, K dan CA0 di bawah. Okay, belah kiri volume lah. Kan kita ingat space velocity adalah initial volumetric flow rate per volume reactor. Dia terbalik, kalau space time, volume per volumetric flow rate, space velocity, volumetric flow rate kepada volume. Okay, so dalam equation ni kamu tengok we don't have volumetric flow rate. So macam mana kita nak rearrange kalau kita tak ada volumetric flow rate? That's why we learn, okay, FA0, one FA0 at the top. If you divide with one CA0 at the bottom, you get initial volumetric flow rate. Sebab tu sekarang saya bahagi satu FA0 di atas, satu CA0 di bawah, saya dapat epsilon naught. So sekarang saya dah ada epsilon naught. So atas epsilon naught, X2 minus X1. Bottom, K CA0. Hanya tinggal satu CA0 lah sebab satu CA0 saya dah divide. Then in the bracket, 1 minus X2, theta B minus X2. So now you have this. So sekarang this is where you need to have further understanding. Okay, volume on the left. On the right, I have the volumetric flow rate. I have the other part of the equation. So I know I want to get space velocity. What I do is I move my volume of my reactor, VCSTR2, I move from left to right. So if I move left to right, it will become bawah lah kan. So it become initial volumetric flow rate divided by the volume. So if I do that, I will get now on my right hand side space velocity. Tetapi the rest of the other things, all the other bracket, kamu dah kena pindah ke sebelah kiri lah. Means I make sure my right hand side is space velocity sebab initial volumetric flow rate terhadap volume. Benda yang selebihnya saya kena pindah ke sebelah kiri. Okay, so I macam switch. So that's how you get now. On your right hand side, okay, yang K CA0 ni pindah ke sebelah sana dia jadi pengatas. So become pengatas, right? 1 minus X2, theta B minus X2 move to the other side, it become pengatas juga. Sebab sekarang dia dah jadi pengatas. The bottom will become X2 tolak S1 lah yang ni. Yang selebihnya dah menjadi space velocity. So now I've already derived the space velocity equation for second CSTR in series. So again, let me repeat. Kalau kamu tengok kenapa equation tak ada dalam notes, memang tak ada dalam notes. Sebab chapter 2 saya ajar half. Okay, chapter 4 saya ajar lagi half. So this is understanding macam mana kamu nak combine information from different chapters for you to derive equation. So that's engineering. Satu macam engineering, it's impossible to know and memorize or to learn all the equations. But as you can see, sometimes half of this equation can be combined with another half or something like that. So that's the challenge for engineering lah. Okay, so this is one of the thing that you have to face actually, the challenge, right? So now kita dah boleh derive equation, tetapi I haven't answered my question yet. Tetapi soalan kata nak apa? Soalan kata dia nak cari the new mole percent of A and B. Sebab kita kata sekarang bila kita nak sambung kedua reaktor dalam the series, kita dah tak boleh guna 60% A, 60% B, 40% E. So apa relevannya ataupun macam mana kita nak cari berkaitan menjawab soalan dengan equation? So then you have to ask yourself, what are the unknowns in the equation that can relevant to the question. Okay, so kalau kamu tengok, okay, sebelah kiri dah space velocity. Of course dah tak ada lah space velocity, kita dah tahu 0.42 per minute. Okay, done. So let's look at the right hand side. Okay, first K. So you know K hanya berubah dengan suhu. Tak ada berkaitan dengan mole percent. Whatever mole percent kamu tukar pun K masih sama. So cannot be about K. Next, CA0. Cannot be about CA0 sebab dah kata dalam soalan part B dia kata suruh guna je CA0 yang sama. So kalau nak guna CA0 yang sama, tak adalah berkaitan dengan equation, tak payah ubah dah, tak ada kaitan dengan mole percent dia. Okay, so next X2. So X2, X1 pun tak ada berkaitan juga because kita dah tahu X2 mesti 0.9, X1 daripada part A is 0.6. It's also something that we already set. Right, so what's left is theta B. So now we think, can theta B be something that we can solve? So kamu kena fikir, theta B, what's the formula? Theta B kan, the easiest understanding is dia adalah ratio of initial mole fraction of B over initial mole fraction of A. So mole fraction kan ada berkaitan dengan mole percent, means kalau saya boleh cari theta B yang baru, I can then correlate kepada YA0, YB0, dan berkaitanlah dengan mole percent because theta B sama dengan YB0 per YA0. I know theta B, I should be able to know what's my YA0 and YB0. Then boleh saya tahu berapa fraction yang baru. Okay, so means in this question, we want to find theta B. We want to find the new theta B in order to solve the question, what is the mole percent, the new mole percent of A and B. Okay, so as I discussed, the rest we already know. Okay, the values already given. We can already get theta B as 1.93. Okay, so now satu lagi masalah. Okay, I told you pula theta B equals to YB0 per YA0. Itu kita dah tahu. Okay. Then now kamu kena faham. Okay, satu equation mesti satu unknown sahaja, only you can solve. So now the problem with this equation, theta B sama dengan YB0 per YA0. Theta B saya dah tahulah nilai dia. Tetapi YB0, YA0 adalah dua unknown. I can never solve. Saya hanya ada satu number. Saya ada dua unknown. I cannot solve. So if you remember, I taught you. Kalau kita ada satu equation, ada dua unknown, your only way to solve is kamu kena cari satu lagi tambahan equation. As long as you don't have equal number of equation to the unknown, you can never solve. So contohnya katakan dalam equation tu kamu ada 3 unknown, kamu mesti make sure kamu ada 3 equation baru kamu boleh solve. You have only one equation, 2 unknown ke, 3 unknown pun, berapa banyak unknown pun, as long as more than one, you can never solve. So means in this case, what I need to do? I have to add on one equation. So tak boleh sembarangan add, you cannot just simply, okay lah kita tambah equation. Tak boleh. So you have to think or you have to figure out what are another equation that I can introduce. Okay, so it come back to pemahaman kamu mengenai YB0, YA0. So YB0, YA0 ni kan mole fraction or mole percent. They are mole percent, right? So you know the total mole percent of A and B, it must be 100% or fraction in term of fraction 1. Meaning YA0 plus YB0 because it's an initial mole percent. Berapa composition yang akan masuk ke dalam reactor, composition dia mesti maximum 100%. So meaning Y in terms of fraction 1. So meaning since only I have A and B, so the YA0 plus YB0 it must be equal to 1. Tu dia punya understanding. Okay, YA0 plus YB0 equals to 1. So now I already have additional equation because I can correlate YA0 to YB0 because I know in my reactor, in my system, these two fractions added must be 1. Okay, so instead of writing YB0, which is additional unknown, I write it in terms of YB0 equals to 1 minus YA0. So now you see, okay, instead of writing YB0, which is additional unknown, I correlate that I know YA0 plus YB0 equals to 1. Therefore, YB0 equals to 1 minus YA0. So now by doing this, you realize I'm only left with one unknown, YA0. So how do I'm left with one unknown? Because I introduced another equation. How do I introduce a new equation? Because I understand I add in A and B, composition dia mesti mole in terms of mole 100%. So now when you're left only one unknown, you dah boleh solve lah because you know theta B, you only need to know YA0. So you can solve, you will get YA0 as in terms of fraction 0.34, in terms of percent 34%. Okay, so what about B? So B kan same concept. Both added must be 100%, right? So if YA0 is 34%, YB0 become 100 minus 34 percent or 1 minus 0.34. Either way, kamu nak kira fraction, you also can. Then kau in percentage also can. You come up with the same. So your B fraction is 0.66 or in terms of percent, 66%. So you see 66 plus 34 is 100%. 0.34 at 0.66 is also 1. Okay, so you have solved the question for part B. So I do admit the question in part B is very, very tough. Okay, sebab the equation is not given to you directly. So understanding of which equation, how do you fit, that's a major challenge lah for the tutorial chapter 4. Okay, so as I told last week, question 5 and 6 I will not cover because I would like you to, when you have free time next week, since we don't have class next week, you have free time, then can you please try to attempt question 5 and 6. Okay, my tutorial question I already provided the final answer. Try first. If you are not able to solve it, then